Welcome back to DemystifySci. I'm Shiloh.
I'm Anastasia.
This is the podcast where we explore ideas that might change the world. We don't know, so we have to sit down and talk to people first. We are on the train from Boston down to New York, heading out to Europe for the Demisticon 2025 experience. But we just got done sitting down with a few different people, first of which is Stephen Wolfram, who you probably know from the Wolfram Alpha online calculation program. We used it a lot when I was in grad school. Wolfram also has a unique model of reality, which is entirely computational. And this is very different than the approach that we tend to study on this show, which is more of a material science approach to fundamental reality, at least at the level of physics, right? So we are certainly not advocating that physics is going to explain everything in the universe, but when we think about physics, we think about it in terms of material science. So we get to sit down and compare notes with Stephen Wolfram about this, and he has a very different conception of how things unfold.
It was a really good conversation. We've been waiting to have this conversation for, I don't know, at least a couple of years at this point. And so it was really cool to be able to do it in person. And so thank you to all of our patrons, all of our conference attendees, because we couldn't do it without you. And if you like what we do, come over to patreon.com/DemystifySci, because that is how we make this podcast happen. We would love to see you there. As part of your patronage, you get to meet with us once a week. We have an excellent Sunday salon that we host and have a great time at. And if you really enjoy the podcast, you should consider coming out to Sesimbra, Portugal for our Beyond the Big Bang conference. If you'd like to come to the dinners in Sesimbra, ticket sales end on June 1st, so make sure you get your tickets now ahead of time. Make sure you reserve your slot. And for now, enjoy the conversation. Tell us what you think in the comments and tell your friends. See you next time.
The scientific revolution starts now.
The DemystifySci podcast.
Let us see in the dark.
So we were having a podcast recently with this woman who was coming up with a physical mechanism that she was purporting to use for finding agency in physics. Like, she was very dissatisfied by the fact that there was no place for free will to emerge inside of physics. And so she had this very complex theory of how this could come from the quantum vacuum. And at some point in the conversation, we got into the subject of, if you have an ice cube that melts in the room, and then you have an omnipotent being that is able to measure every single water molecule and its trajectory, can you reconstruct the ice cube in the center? And we spent some time on that. And then as we were thinking about this conversation...
I believe I threw in at some point, what if the ice cube was shaped like a starfish? Could you still do it?
And it seems like this is something that you are deeply, that your work is deeply pointed at, which is that there is some aspect of nature where even if you know everything about a system as it is right now, you can't necessarily get back to the starting point. And so I wonder if you couldn't make that case for us for why that's true.
Well, it's a complicated story.
Okay.
Right? So let's see. We're talking about, the fundamental phenomenon here is second law of thermodynamics, law of entropy increase, kind of something that was actually a thing that got me started on a half-century trajectory of, I got interested in kind of the second law when I was like 12 years old, and even started trying to simulate things about idealized molecules and so on a computer. Didn't work out very well at that time. Later on, I realized that actually I discovered something more interesting than I thought, but I did not have the kind of context. I hadn't figured out the context to be able to understand it. But in terms of this question of kind of, you have a system and you know sort of the microscopic laws that make gas molecules bounce off each other and so on, what does that mean about what you can figure out about how the whole system works? There's sort of a fundamental thing, I call it computational irreducibility, and it has to do with this question of, even if you know the rules for something, can you know everything about what the thing is going to do? And one of the sort of ideas of that people got used to in mathematical science was, post Newton and so on, was we're going to use math, we're going to write down a formula for how certain things work. Once we have that formula, we just know everything about how the thing works. We can just say, 1 million years from now, we plug in the number of millions somewhere, we know what's going to happen. That had been the kind of dominant view of sort of how science is supposed to work. We can figure out a formula. We can work out everything about what's going to happen. What I realized is when one's dealing with things which one thinks more in terms of programs, more in terms of sort of rules that you just keep applying one step after another, it's not so obvious that's going to work. And so what you then have to believe is that if you have some rules, they might even be quite simple rules, and you just apply them step by step by step. You apply these rules. The question then is, can you jump ahead? Can you say, this is, even though the system did 1 million steps, can I be smarter than the system and sort of know immediately this is what's going to happen after 1 million steps? And so the idea of computational irreducibility is that's often not possible. It's often the only way you can find out what the system is going to do after 1 million steps is to run those 1 million steps and see what happens, which is something that is kind of, it goes against the kind of the assumption about what was going to be possible with predictive science and so on, which came from this kind of mathematical tradition where it's just like you write down a formula for the answer. So in terms of your ice cube and so on, what happens is you have all these molecules, and they're individual microscopic laws of motion. We can perfectly well understand. We can reverse them. We can do all kinds of things with them. But when we have a whole bunch of molecules together and we say, well, what's the computation that's done by all these molecules, colliding with each other? That computation can often be an irreducible computation where to know what will happen, we just have to run each step. So why is that relevant to sort of what happens with thermodynamics and entropy and all those kinds of things? Well, it's like you start off with these gas molecules in a particular configuration, you run the rules, they do what they do. Then you can ask a question like, well, the configuration that they're now in, is there a trace that they all started in the corner of the box, for example? Or is there no trace of that anymore? Well, the fact is that if you were able to trace every molecule, there absolutely is a trace. You just run the rules backwards and you can kind of see that they all end up in the corner of the box. The issue is that if there's computational irreducibility, it's as if that process of those collisions and so on has sort of encrypted the initial data about where the molecules were to the point where when you as an observer try to reconstruct things, you kind of have to do all this computational work to figure out what happened. And as a practical observer, just making, your measurements and so on, measuring pressures and all this kind of thing, you can't do that. Now, if you had instead of a pressure measuring device, which is some great big, paddle that's measuring pressure, you had something that was able to touch all those individual molecules, then you would have enough data, but then you would still have to run this computation that corresponds to all those collisions of the molecules. You would be basically reproducing exactly what the molecules did microscopically as a practical matter with macroscopic kinds of materials, and more importantly, with the kinds of measurements that we make. You can't do that. And so that means that the only thing you can say is, oh, these molecules, what happened to them? Oh, they just, are doing random stuff. That's the best you can say. You can't say anything better than that because you can't sort of do the computation to decode what happened. And so that's kind of why, the law of entropy increase, for example, the notion of entropy, entropy is basically counting the number of states of a system that are consistent with whatever you know about that system. So if all you know about the system is it's all the molecules are in the box, there are many, many configurations. If you know, oh, these molecules are arranged in this particular way in the corner of the box, well, there might just be one configuration that's consistent with that. And so the issue is, given what you can actually measure with actual measurements that you are sort of computationally capable of doing, can you figure out what's true about these molecules? And the point is that with the kinds of measurements we can make, which tend to be, among other things, computationally limited, you can't, because of computational irreducibility, you can't figure these things out. And so you have to just say, oh, the only thing we can tell is that the molecules are all in the box, for example. And that means that the entropy that we assign to that is where we just give sort of, let's say, equal weight to all the different configurations that the molecules can be in. So that's why it sort of seems to us that entropy is increasing. I mean, there's a thing that people, back in the 1860s, where people were first kind of sort of really formulating the second law of thermodynamics, very quickly people said, and this will mean that the universe has a heat death in the end. The universe, right now, we're doing all these cool things in the universe, but in time, just like your, water molecules in the ice cube or something, in time, everything will turn to randomness. And they said, and they had, at that time, they had an interesting kind of issues with sort of theological kinds of things that they were also thinking about. That's a separate story. But the main point was that their belief was everything will just become random. Now, point is, it only becomes random with respect to an observer like us. To an observer who can really see all the details of those molecules and really do all the computations, that observer in the distant future, when everything is sort of run down, it's all turned into heat, that observer will say, actually, no, these molecules are not just typical of all possibilities. These molecules are configured in just this amazing way that corresponds to the fact that at this time in 2025, these people were sitting and talking about this, and this is the future of that, so to speak. But it's to an observer like us, with our level of kind of coarseness and our kind of computational boundedness, to an observer like us, they're right. It looks like randomness. But it isn't really that way. It's just that's the way it looks to us. I mean, this point about sort of the way things look to observers like us is, I think, pretty important in understanding why physics works the way physics works. I mean, I if you'd asked me 10 years ago or something, would one be able to derive the laws of physics? I would have said, no, the laws of physics are the way they are because we just got dealt this particular universe, so to speak, and we can't really say why they're the way they are. If you'd asked me about the second law of thermodynamics, I would have said, well, that's a different story. That one might be derivable from something lower level, from just knowing about mechanics plus some sort of math-like thing. In fact, I already knew at that time kind of how I thought the derivation of the second law would work. What I didn't see coming at all was the fact that general relativity, theory of gravity, and quantum mechanics would also end up being derivable. And that's kind of that's my biggest excitement for the last few years is sort of the belief, the conclusion that physics is the way it is because it has to be that way for observers like us. If we were different from the way we are, physics would seem different to us.
Different how?
Well, it's, for example, let's take the example of the heat death of the universe. We believe in the second law of thermodynamics because we are computationally bounded observers who just say, when the molecules do their thing, they just kind of throw up our hands and say it seems kind of random now. But to observers who are not computationally bounded, they would not come to that conclusion. They would not believe in the second law. That's a feature of the interaction of this sort of fundamental phenomenon of computational irreducibility together with the way we are as observers. It's not a feature of all possible observers. It's a feature of us as observers.
Do you have a model, though, of what it would look like for somebody to be an observer that's not computationally bounded? Because as far as I understand computational bounding, it's that, like you said earlier, if you have a system that has 10 million particles in it that have each a million parameters that describe whatever their state is, the reason that that's computationally irreducible is because we just don't have a computer that can run that.
We don't have temperature and pressure sensors that are down at the atomic scale either.
Yeah.
Right. But it isn't just a question of what you can measure. It's worse than that, so to speak. It's a question of whether you have to sort of, if you've got a bunch of black and white squares or something and you're making some pattern, do you end up having to see what every square does? Or can you say, oh no, I know the big picture, I can know that this thing will eventually make 3 black squares at the end or something. It's that even independent of these questions about whether you can measure all the initial data, you can even have situations where you can know enough about the initial data that if you could do the computation, you could figure out things about what comes later. What's important is there's sort of this inexorable, it's actually the foundation of what time ends up being. Time is this process of the universe computing its next state. I mean, in other words, the progress of time is the progressive computation of states in the universe.
Would you say it's like a frame in a movie?
Not well. Which is the frame? I mean,
the frame is the states of everything in the universe and the information about where they're headed and their properties, which then time is
That's 2 frames at least.
That is, time is at least 2 frames of.
Well, so it actually is a little bit more complicated than
Okay.
that, because we can get to this, but when relativity tells you there's something a bit more complicated going on, because time is not this thing where the universe is where you can just say, here's the frame, this is the universe now, and this is the universe later. There's this whole question of what counts as now across the whole universe.
You're talking about special relativity.
Yeah, in special relativity.
And simultaneity.
Yes. So it's a little bit more complicated than that story. But if you ask kind of what is the sort of fundamental thing that's going on when time progresses, it's the computation of later states of the universe, so to speak. So
why do you call it computation? Because for me, computation is a calculation, or is something that is. And this could be totally naive, but when I think computation, I don't think just the product of interactions. I think of the prime mover, I think of the programmer, I think of the microchip. Is that...
If I lived in a different age, I probably wouldn't call it computation. Computation is the best metaphor given the age that we live in today. So in other words, it's in another age, I might call it whatever you call it to tell an army what to do. The rules that you use to tell an army what to do. But that wouldn't be a thing of our time, so to speak.
Steve Wolfram's Art of War. Okay.
Right. Maybe what goes into a computation? So you have some axioms, you have some inputs.
Well, so as far as I'm concerned, a computation is just you have certain rules that say how you get the next state of a thing from the previous state of the thing.
So how you integrate the information?
Well, in the things I tend to study, you've just got, a line of black or white cells, and it just, the program just says, if you've got black, black, white, then at the next step, the middle cell turns white, for example. That's a very kind of minimal type of program. And so the computation is then the running of that program, the applying of those rules. That's the process of computation, so to speak. Now, I have tended to, in recent times, I've kind of been talking a lot about what I call ruleology, the theory of it's a very foundational science. It's probably might even be the most foundational science, because it's the theory of what simple sets of rules do, what the consequences of simple rules are. And those rules can have any form, but it's kind of convenient to state them in ways that we can visualize in terms of black and white squares or whatever else. You can state them in terms of more abstract sounding things, but that's the notion. And this idea of, you say, what is computation? Well, computation is the following of definite rules. Now, what's not obvious is whether that adds up to anything. In other words, it could be you follow these rules and you go to a lot of effort, you follow all these rules, but somebody looking at it from the outside could just say, why'd you do that? The answer is 17 or something. We can see that from the outside, so to speak. So I think the thing that makes computation really a robust thing is this idea of computational irreducibility, because the fact that there are irreducible computations where you have to follow each step to see what happens, means there's sort of no way of getting around the computation, so to speak. And that's that idea that there's sort of this uniform notion of getting a computation done. That's an idea that's sort of important in thinking about computation. It's also an idea that's important in thinking about time, for example. It's sort of the reason, I think, that there is an invariant notion of time, that time for the universe, time for our brains, time for other kinds of things, is there's something that is happening that is sort of happening kind of the same way in all those different systems. And that's this sort of progress of computation, so to speak. I also think, you mentioned free will. Computational irreducibility is closely related to that whole story, because you might say, oh, I know the rules by which some system is going to operate, so therefore I know everything about it. If you look at the science fiction movies from the past where there were, robots involved and so on, it's like, this robot is following logic, therefore we know exactly what it's going to do. Now, anybody who has experience with modern computers knows it doesn't quite work that way. And that's kind of a version of computational irreducibility. Just because you know the underlying rules doesn't mean you can immediately say, oh, I know what it's going to do. You have to follow each step. And
Does each step correspond at any given moment to all of the individual actors that are in your system? Like, do you have to have a different set of rules for each actor in this system?
No, I mean, in many things, okay, so in ruleology, so to speak, it's a very sort of pure basic science, and one can just talk about things in terms of black and white squares and so on. If we were doing this to understand something about biology, we might have a different setup. If we're doing it to understand things about fundamental physics doesn't, I think, is not well represented by black and white squares. The things that represent what's underneath space and so on are more abstract. They're a little harder for us to kind of wrap our brains around. So it doesn't end up being kind of just this quite that same story. I mean, we'll talk about this, but kind of the structure that I think is, in a sense, the universe has the least structureful structure underneath it.
Interesting.
And so, but the things that
could that just reflect our inability to grasp the uncertainty, the statistical nature of what we're seeing and what we're modeling at that scale?
No, I think it's a question of, I mean, you know, to talk about sort of what is space, for example. I mean, this gets us off onto another, but let's finish on free will for a second, and then we'll talk about space.
We'll come back to
space. Yeah, don't forget space. Leave a space for space.
Space for space.
On free will, I mean, there's this question of if you can predict what something is going to do, you won't consider that it has free will. If you knew this moth is just going to keep, you know, bashing itself in this way, and then you're going to say it doesn't have free will. But if you're in a situation where the only way you can work out what the thing does is to do the same as it's doing itself, then that's a story where it seems to be independent in the sense that you can only know what it's going to do by just following the exact things that it's doing or just watching what it does. And I'm pretty sure this is kind of the story of what, you know, for all of us, this is what's going on. That is, if you could figure out, you know, if you could have a computer that's running all the neural signals in our brains a bit faster than they're actually running, then wouldn't look like we have free will, because it's, you know, you could say what was going to happen. But the fact is, there is this irreducible computation that's going on where there isn't going to be an easy way to do that. To do it, you really have to follow each neuron, you know, figure out what it's going to do, and so on. I mean, this is becoming rapidly very practical, because there's a little company that I was just talking to that's interested in, you know, uploading brains and things. And so it really starts to matter, you know, the fly connectome was recently decoded. So at least the connectivity is known. I mean, it's not clear the connectivity is enough. You know, you have a nematode. We've known the connectivity for ages, but we still don't know how to make a nematode do what a nematode does by just simulating its neural net, so to speak.
So there's no space for coin flips in the brain in your model. There's no space for.
There doesn't need to be. There doesn't need to be. I mean, I think a lot of what happens in brains is, I mean, the question of, as a practical matter, you know, how deterministic are brains? That's a slightly different thing. I mean, we have to worry about, you know, to what extent do we have are we affected by heat and things like this? That's, I think, that's
cosmic rays.
Yes, but I mean, you know, if you look at an LLM, for example. An LLM can be perfectly, you know, can be doing very human-like things, but yet it is completely deterministic. But it is also not possible for us to predict. If you say, what's that LLM going to write next? Well, really, the only way to find that out is pretty much to run the LLM and see what it does. There's no sort of theoretical model that lets you say, you know, I've solved the LLM. I know it's going to.
Yet it's still following a discrete set of rules.
That's correct. Right. So it's some now, you know, and
they also don't seem that deterministic. Like, you can open new instances of the same LLM and ask the exact same question worded in the same way, and it'll give you different answers.
That's because of a hack. It's the so-called temperature parameter of LLMs, where you know what an LLM generates. For its, you know, next token prediction, it generates probability distribution across like 50,000 words or whatever that there are in English. And for every one of those words, it tells you, this is the probability I think that the next word is going to be fish or whatever. And then you as the sort of the system that's kind of running the LLM get to choose, well, which actual next word should I choose? For example, you could say, I'm going to choose the one that the LLM says has the highest probability. That's what most LLMs today that write code do. The ones that write text, it's been discovered that it's a bit more kind of human-like if you have a different temperature parameter, which allows you to kind of sample some of the lower probability words with non-zero probability, so to speak. So it's really
it's just fluctuations, essentially.
Yeah, it's just a thing that has made it seem, if you run a text generation LLM in a deterministic mode, it is even flatter than it is when it isn't in a deterministic mode. And I mean, footnote to all of this that is really complicated is even if you're running them deterministically, as a practical matter, they won't always do the same thing because of the way that GPUs work and because of the fact that there are optimizations in GPUs that depend on GPU state. And this is just a complicated mess. It took me a while to figure out what was actually going on, because it was very confusing to me that you could run an LLM, and I had to ask sort of the originators, so to speak, to really nail down what was happening. And it's a detail about essentially operating systems running on GPUs.
But doesn't that undermine the entire idea of determinism if you've created this complex program that you then run on very straightforwardly strict hardware where even there's enough noise that you don't get the same answer and it's run in deterministic mode? Why would you expect to have determinism in something as squishy and faulty and susceptible to small tweaks and temperature fluctuations as the brain?
The brains, we don't get to do this experiment on brains, at least not yet.
Sure.
So, and as a practical matter, the question is it important that, brains have kind of, is the thing I'm about to say next more determined by the deterministic structure of my neural net, or more determined by that little, piece of heat that ended up in my, parietal lobe right before I said the next word, right?
Yeah.
What about the environment itself? What about the chaos of our interjections or
that certainly has an effect on this question of whether what brains do is, will we have a fully deterministic brain-like thing? Well, the answer is our neural nets, insofar as they're doing brain-like things, are, they're digital electronics. They're easily sort of deterministic. I was mentioning that weird footnote, but basically they're deterministic kinds of things. The question of how important it is to us that we have other influences that are coming from the environment, I don't know. I mean, my guess is that the vast majority of what's going on is fairly deterministic. But how important that occasional, am I going to do this? Am I going to do that? Well, there's some knife edge that you might be on where it's like, this is the case. People talk about sort of the chaos phenomenon, and people, that got a bit confused because people said, oh, well, whether the storm happens or not depends on this butterfly. Well, there is a very tiny possibility that the butterfly will be the decider of whether the storm happens or not. But the vast majority of time, the butterfly doesn't make any difference at all. It's just that very weird sort of knife edge on which it makes a difference. And the mathematics of things, I mean, this is a story of kind of, it's actually a bit of a confusion in terms of how the mathematics works out. There's a certain tendency which, sort of repeated in the history of physics, among other things, is that sometimes the math works out really nicely, it's really cool, just turns out that the thing that it represented isn't what you thought it represented, and it's all kind of not set up correctly. I mean, I think this happened, for example, with space and time. It's a place where I think this happened. 1919, I think, was sort of ground zero for this problem. Was, Einstein had come up with relativity. For Einstein, space and time were different kinds of things. He had arguments about how they were related, but they were still different kinds of things. Then Minkowski said, well, I can make this quantity that's, x squared minus c squared t squared that represents this nice object, this nice mathematical object. He'd studied quadratic forms, which are of that mathematical structure, said it's a great quadratic form. Space and time are really the same kind of thing. We're going to bundle them together in this quadratic form. And, from that time on, a lot of people kind of took it as being sort of the thing that physics says is that space and time are the same kind of thing, which I think they're really not. I think they're really quite different kinds of things. And understanding that is important to understanding how physics actually works underneath. We talked a little bit about what time is, which is, I think, the progressive computation of future states of the universe. And so a big question about space, yes?
Is there an initial condition for this computation? Like, is there time? Is there a T0?
That's a complicated story.
Okay, let's come back to that.
In the simplest case, you could think about there being an initial condition, but the full story is more complicated than that.
Let's do space first, and then we'll come back to time zero.
Right. In terms of what is space, right? So, back in antiquity, right, there were the atomists, there was Democritus, there was Heraclitus on the other side. It's like, are things made of discrete atomic stuff, or are they flowing like fluids? And people didn't know. And that, debate.
And they didn't know that fluids were made of discrete stuff either.
No, they didn't. They didn't. That became, people started saying that in the 1600s, people started saying that. But they, this question of, is it continuous, is it flowing, is it discrete, is it made of atoms? That was sort of a big debate of antiquity. And it remained a big debate until the end of the 19th century, because nobody knew that whether matter was discrete or not. Actually, that got resolved around.
Aren't people still fighting about this? We're fighting about this all the time.
Whether matter is discrete, I think that's pretty settled. There are molecules, there are atoms. Well, that's what matter is made of.
But then you start pressing on, like, the outer surface of the atom is the electron, and the electron is described by a wave function, and there's the electric field, and so you get into field dynamics, which seem somehow more on the continuum side of things, and so there's a sort of blurring of the line between.
Yes,
because you're still shooting electrons around and.
There's a notion of a discrete thing that is the electron. And the question of sort of where is that electron and so on, how do you represent where the electron is, that's a different story. But as far as you can count electrons, that's a thing. You can count them. You can count atoms. If everything was just flowing continuously, you couldn't count atoms. And so similarly, end of the 19th century, people had discovered things like Brownian motion, and it was clear there were like discrete kicks to those pollen grains that you could see under a microscope. There's something discrete going on, that the water is discrete, is made of discrete stuff. Then, photons came along and it became clear you could think about light as discrete. So beginning of the 20th century, most physicists, if you'd asked them, what about space? They would have said, well, it's going to be discrete too. And that was the belief of basically, it's a weird piece of history, which I've only been sort of decoding. I have to write something about it at some point, because what's strange is, because it didn't work, almost nothing that those guys thought about got written down in a published form. And so it's been a whole bunch of weird little...
You're talking about the ancients.
No, I'm talking about people like Einstein and Bohr and Heisenberg. They all tried, there's like a few letters from Einstein where he says, well, yes, in the end, space will turn out to be discrete. But he was smart enough to say, but we don't have the tools to understand how that works yet.
But do you know what he was thinking about in his mind when he was saying that it would be discrete? Like, did he ever describe the picture of what that is?
Not really, but I know what Heisenberg tried to do, for example. But for Einstein, the main thing was, for him, it was like, okay, we've now discovered that molecules are a real thing. You can interpret Brownian motion, it's molecules. Okay, for light, the introduction to his 1905 paper about the photoelectric effect is pretty clear. It basically says, we've now discovered that matter is discrete. Let's apply the same ideas to the electromagnetic field. Okay, so then, his assumption was then, and we're going to be able to do the same thing for space. But it didn't work. So Heisenberg had a model that was actually quite similar to things that I've studied in quite different contexts, although I had no idea until recently that he'd done this. But and I think it maybe some archive trips are needed there, because I haven't nailed it all down. But he had kind of a let's imagine that space is sort of made of little discrete boxes, and sort of think about things that way. That kind of doesn't work when you're dealing with relativity, because relativity kind of doesn't let you have a discrete fixed structure of space. It's not consistent with how relativity works and what's observed experimentally about how that works. And so,
is this because of the field approach?
No, it's just because if you have if space is absolute, then it's made of little boxes. Then when you have something like, I don't know, the contraction effect, when you have a fast-moving object, it doesn't get to contract because it's made of these fixed boxes. It's kind of, you're stuck with space as it is, which isn't what relativity says is going on. So that it's very, it's a very sort of practical mathematical issue. So, I mean, the thing that I realized, I don't know, first in the early 1990s, but then really sort of made it work 5 years ago or so now, is there's the sort of the most structuralist thing one can imagine that the universe is made of is something which is kind of just a whole collection of discrete points, kind of atoms of space. That the only thing you can say about an atom of space is that it exists. It's kind of an atom of existence, and it is distinct from other atoms of space. And the other thing you can say
Does it have a distinct location at any moment?
Well, it doesn't have a notion of location because it is just
location.
Yeah, but it
is only location,
right? So the thing is, what you can talk about is how these atoms of space are related to each other. And so then what you can do, if you want to represent it kind of mathematically, is you draw a graph, a network that just joins, every atom of space to its friends. And that builds you up this big net of atoms of space. And that's the definition of what it means, where it is. It has no absolute notion of where it is. All it knows is how it's related to other atoms of space.
What's the difference between an atom of space and an atom at that location? Like, could you build this if atoms were...
Atoms are really, really big compared to the atoms of space.
See.
I mean, the atoms of space are... So in this model, kind of everything in the universe is just made of space. So it's kind of every feature, all the universe is this network with these atoms of space, atoms of existence that are related to each other.
Are they made of anything?
No.
Do they have structure or form to them?
No, they are abstract, idealized objects that are
very
whose
platonic.
only yes, it's very platonic. Whose only the only thing one could say about them is that they exist and they have these relations to other ones. And so the thing that if you ask, well, what's a picture of what an actual atom might be like? Okay, imagine you're dealing with a fluid. Fluid has all these discrete molecules inside it. But then you have an eddy in the fluid, some little vortex that's going around. That eddy is made of lots of different, molecules at different moments, but the eddy has some persistent existence. That kind of persistent existence is what I think is how things like electrons work. It's also how black holes work. I think there's a close relationship actually between black holes and things like electrons, but they're all just features of the structure of space. And so the only thing you can say, the only thing that exists in the universe is space. And everything that is sort of the material structure of the universe is features of the structure of space.
So how do you get from something that doesn't have shape or structure or location?
Only a location.
Well, it doesn't have a location. It doesn't have a defined location. All it is just, it's a thing. It's this network. And let's just imagine that the network was like a fishing net or something, where it was just a grid, where everything, it's a bunch of identical little cells. Okay, if it was like that, then you could reasonably say, even if the fishing net was all crumpled up, you could still imagine what it would be like if you stretched it all out. And then you could say, well, I know this particular atom of space is at this location because I can make this sort of coordinate system of where all the different pieces of the net go. But the fact that the thing is there doesn't depend on, that's just my version of how to explain what's going on. It's not what it intrinsically is.
It's your model.
Yes, this is a model. Well, this whole thing is kind of a model for the structure of the universe. And the question of what you could ask questions like, how do things emerge from that? So it's just like in a fluid, for example, you might say, how do you get anything that you could sort of count in the fluid? Well, you can get these little eddies, and the eddies can go along and they can move and they can interact with each other. And you might say, if you were looking at the fluid from the outside and not knowing it's made of molecules, you might say, those are the real things in the fluid, are just these eddies. And so it is with what we observe in the physical universe. We're mostly saying the real things are things like electrons. But those are very huge emergent objects relative to what the underlying structure of things actually is.
Doesn't that leave us with the same problem that we have with something like particle physics, which is that there are these mathematical wave-like observations of field effects that are not physical, but that then produce physical phenomena? Like, I think that I've heard Barandas call this like the Heisenberg gap. Like, how do you go from the mathematical abstractions to stuff? Like, how do you cross that gap?
Well, so that's okay. So what do we know about the universe? What we know about the universe is what we perceive from the universe. And so the real question that we have to answer is, we got all these experiments we do, we got all these things we can see. What we really want to do is to have a theory that tells us, what are we going to see in different cases? What are we going to perceive about the universe in these different cases? And if we say that you can ask sort of what's really there in the universe, we can go a little bit further and we can start saying, this is a good model for what's really there. What we can tell about what's there is what we perceive from the universe. We can ask, if we're saying what's, quotes, really there, that's a philosophically slightly complicated thing, because in a sense, what we're talking about is, okay, the universe is doing what it's doing. When we try and make a physical theory, what we're trying to do is make a bridge from what the universe does to a narrative that we can understand in our minds.
Absolutely.
So we're trying to make this, we're trying to take what the universe actually does and crumple it up and sort of make it fit in our finite minds. So, for example, a lot of what the universe does, we may never be able to fit in our finite minds. That's kind of what computational irreducibility is telling one. There's a lot of detail about what the universe does that will just not fit in a finite mind. And so what we get to sample are only certain features of the universe that we choose to consider important that will fit in our finite mind. So in the example of the second law of thermodynamics, we're not sampling every individual molecular position, we're just sampling the temperature and pressure of a gas or something. And that's something we can talk about in our finite minds, and we can kind of have a whole physical theory about that, about how pressure and temperature depend on things.
So you're sort of saying that viewing each point in space as its own atomic entity is kind of the closest we can hope for in terms of approximating what's happening at all points in the universe.
Yeah, well, I mean, the way to think about it, I think, is that this is an attempt to explain the universe is doing what it's doing. This is an attempt to make a bridge that is understandable to us about what's actually happening in the universe. Now, this talking about hypergraphs and atoms of space and so on, there are different ways to formulate this. That are there are ones we already know in terms of higher category theory and so on. They are to most people much more obscure. This is, the idea of atoms of space and connections between them and so on it leverages our kind of mechanical experience of the world to some extent. It only goes a certain distance because there are features of the very microscopic world that are not very familiar from the world as we know it right now. But we could all equally well talk about things in terms of some limit of some weird, higher category, something or other thing, which happens to be much less familiar to people than these things about fishing nets and so on. And so but what you have to understand is all of those things are merely descriptions. They're merely ways to kind of take what to take this thing that is kind of our, what the universe is actually doing and try and get it so it fits in our finite minds.
Yeah, I think an explanation has to organize descriptions fundamentally at the end of the day. If you're going to make sense of something, you have to order all of the different pieces that you've broken down into something that has a narrative to it. That's just the way that our minds work.
Well, our minds are very finite. I mean, this is I was just actually working on a little effort which I thought was going to be really straightforward, which was what if our minds were bigger than they are? What if our brains were bigger than they are? Because we know, the very obvious fact about the world is cats don't talk. And
Our cat talks a lot.
She does, but she doesn't speak
She doesn't speak
Shakespearean
English,
poetry.
yeah.
right, compositional language is not for cats, so far as we can tell, right? But we have much bigger brains than cats. Our brains are only 100.
Quite a few more neurons.
Yeah, we have 100 billion. They have maybe 100 million. So it's 1,000 times bigger.
I think about roughly the number we have in our intestine, if I recall correctly.
Is that right?
Something
Okay,
like that.
that sounds plausible. But in any case, so something changed as we went to bigger brains, and the question is, as we go to even bigger brains, which we can start thinking about with AIs and so on, what kind of things will happen? And the thing that one's really struck by, I think, is the universe does what it does. It has all these computational processes going on. Our brains have computational processes going on. But actually, one of the things that's fairly striking is the computational processes in our brains are deeply limited. And they seem to be limited in one very particular way, which is, we have a few million sensors from our eyes, our touch sensors and so on. They're coming into our brain. But our brain's main goal is to figure out what should we do next.
Mm.
And one of the things that, brains seem to emerge when animals emerged. And, animals need to know, they move around, so they need to know, where am I going to go next? And one feature of an animal deciding where it's going to go next is it has to go to a definite place. The animal can't just say, I'm going to go to 1,000 places at once. It's just like, I've got to decide, I'm going to go to a definite place. So a lot of what happens in the brain seems to be taking all these stimuli and maybe 10 times a second or something, concentrating them down and saying, okay, I'm going to take sort of a majority vote. I'm going to decide what I'm actually going to do next. And this concentration down of things, I think, is very characteristic of sort of the way that we observe the universe. And I think that the thing to understand is the full kind of computationally irreducible processes that are going on in nature are not the kinds of things that happen in our brains. Our brains are very limited. We might have hoped that we're kind of the pinnacle of everything. And, we're doing more sophisticated stuff than the rest of the universe. It's really the other way around. We are doing things that are fairly specific. We're doing a particular kind of computation that tends to go to concentrate things down, to say, for us, the precise details of what pixels I'm seeing in my visual field don't matter. It's just roughly I'm seeing this person and so on. And that's what I make the decision about what to do next based on. So this idea that we're sort of compressing down the input that we have. So we're not doing general arbitrary computation. We're doing sort of this fairly specific sort of observer-style computation that that kind of concentrates down to answer the question, what should we do next?
It does seem to be very effective to do that, though, doesn't it? I mean, you look around the room, and if true full-bore computation is the gold standard, it seems like we've come pretty far with this deeply focused, filtered way of seeing the world, given all of the things that we have in front of us, given all of the pieces that the technology,
it looks very impressive, yes, but it isn't very. I mean, if you think about the air molecules in this room, they're doing much more sophisticated computation than we're doing. In other words, the things that we have identified...
Are they just getting out of the way of each other? I mean, couldn't you just boil their computation down to being displaced by one another?
Well, you could boil down the computation that happens in our brains to a bunch of electrochemistry, but we think it's more significant than that. In other words,
you also have all of the other actors, right? I mean, humans are incredibly complex social beings, right? You can torture a human by putting them in isolation.
Right, but I mean, the fact is that the things that we think are significant about the things we do are things, nature does a lot of stuff. And there are certain aspects of nature that we think are significant. And just like with the second law of thermodynamics, we think, pressure and temperature of gases is significant. We don't think some microscopic feature of how molecules dance around is significant. So to us, the things that we do seem significant. To the universe as a whole, in some sense, it doesn't have probably a view in that same sense of what's significant and what's not. But we are slicing off some piece of what happens in the universe that we consider is significant to us. Now, that happens at the level of, it happens in thermodynamics, it happens in the structure of space-time, because for us, we could say we worry about what this hypergraph that represents the underlying structure of space is like. We don't. At our level, we're just like, space seems like more or less a continuous thing. We can, for the purposes of our minds, we can view space as just being something that is, just an approximately continuous thing, even though at a microscopic scale, it's made of all these atoms of space and so on. I mean, another thing that seems to be very important in the way that we perceive the universe is that we believe we are persistent in time. So if we're at every moment in time, we're actually made of different atoms of space. Just like that eddy moving around in the fluid is made of different molecules at every moment in time. But yet, we have this perception that we are the same us as we were a moment ago. And in fact, our brains go to a lot of trouble to arrange us to have a single thread of experience. It is a surprising thing. We've got 100 billion neurons firing at a time in our brains. How come we think a definite thing happened? It's surprising. And the brain's architecture is such that it concentrates everything down to say, this is the thing that is the definite thing that happened, so to speak. This is the thread of experience. We could have brains that believe in many threads of experience. I mean, this is what happens between different humans. Different humans have a different thread of experience that only gets connected rather weakly by talking to each other or whatever else. But within our brains, we could have, and when it happens that way, it's kind of pathological. We could have multiple sort of people in there, kind of all having a conversation. But that's not how it works in normal, in the normal psychology of humans. And I think that's it's another kind of way in which sort of our brains are not being as computationally sort of sophisticated as they could be, so to speak. They're just doing this thing that has a single thread of experience. And
what would it look like for our brains to be more computationally sophisticated? I guess is what I was trying to get at. So it's like we've done all of this with the computationally unsophisticated brains that we have.
Well, look at what the universe has done. It's made all these planets and stars and all this kind of thing, and it's not got brains in it. It's just got physical processes. I mean, it's rather amazing that the universe can make a pulsar or something, and it did that by just to us, the things we make seem interesting, remarkable, etc. It's it sounds very depressing that we go to all this effort as humans, and yet in the end, what did we achieve, so to speak? And I think that the thing to realize is, once you realize that sort of you can think of everything in terms of raw computation or whatever, we represent a particular prong in the world of raw computation, and for us, that prong is really important. I mean, we could imagine some sort of alien intelligence for whom some completely different prong was important. They look at our prong and they're like, what are all those, what are they doing? Why are they arranging, why are they building these square boxes that make, houses and things? Don't they know that, if you could just look at the gas molecules and how they form these things, that will be much more significant to them. It's a feature of we do things that seem significant to us. And, you see that in more abstract ways in the development of, let's say, mathematics. There are particular directions that mathematics has gone in, but it didn't have to go in that direction. It's an abstract thing. Sometimes it's grounded by things that we know about physics, but often it's just off doing its thing. And it could have gone in different directions. It's just that direction was something that we humans decided was important and aesthetic and whatever else. But it's kind of arbitrary at some level.
I'm intrigued by this idea of subunits, and I've always been intrigued by it in terms of atoms, right? Because we know that atoms change shape. And for me, like, my background is in material science, elastic mechanics, and atomic force microscopes and driving cantilevers and all of this, and I'm keenly aware that deformation requires subunits fundamentally, and that the sort of nodal interactions between the subunits ultimately dictate the shape changes that are possible. And so I'm intrigued by the idea that the atom, and let's say its connections to other atoms, would have some sub-architecture to it. What I'm curious about, wondering if we can bridge, is that it seems like you've sort of resurrected this Boscovich point atom system, where there's locations that have an influence on their neighbors in an interesting way, but there's no real actors there doing this job. Do you imagine that either A, it's unimportant what those actors are, or B, that you just don't believe that there need to be actors at all at the substrate level?
See, one of the things that's tricky is that when you're thinking about things about what the universe is sort of fundamentally made of, our kind of everyday view of you deform this and things move and so on, you can't really apply that kind of intuition. The intuition is different because you say, I think it is hard to wrap one's head around the idea that things aren't in a particular place. All that one can say about them is how they related to each other. So, in the case of you're asking about things like, I'm
sorry to interrupt you, but do you mean when you say all that you can say, is that the same as that they are not so? For instance, like the statements we can make about reality, those may be limited in a way that don't reflect what is actually happening. We may only be able to say so much. And
because we've said that reality is computationally irreducible for us.
Right, but does that still implies that there may be something defined and objective and material at the core of these interactions?
No, you see, the thing is, this is the whole story about what models actually are. This is the thing people seem to often have a lot of trouble with. A model is this bridge between the universe as it actually is and the narrative that we can put in our minds. And so if you start asking, well, is it the narrative? No, it's not the narrative. The narrative is what we get to put in our minds. It's just like in the kind of Newtonian paradigm, it's like there's a mathematical equation that describes the motion of the Earth. It is not the case that the Earth has a little, copy of our Mathematica software in it that's going and solving these equations. It's just that as a description for our minds of how the universe works.
Well, it's a description of how it unfolds, but, even Newton famously said he had no idea why it did what it did. Like, he didn't understand, he wasn't able to explain the cause of the gravitation, only that it unfolded predictably in this universalized fashion.
And he was basically like, once we have enough data, we really ought to
subtext
try.
Well, okay, so I'm a slight expert on Newton, but not a complete expert on Newton. One of my things I learned about Newton recently was he predicted the world will end in 2060.
Uh-oh.
So and he has a whole calculation based on that.
The Wolfram death cult is still coming.
Yeah, right. Anyway, but Newton was, remember the title of his big 1687 book is Mathematical Principles of Natural Philosophy. And the big pushback about that book was, what do you mean there are no angels pushing the earth, so to speak? That there's no mechanistic thing that you're describing about how the earth, how things work, that it is merely mathematical principles, not a mechanistic set of ideas about how things work. Still, in biology, for example, a lot of biology is still very mechanistic, very much, this lever pushes this lever, and that's how it works, so to speak. It never really made the jump to the theoretical mathematical theory that physics made the jump to. And it's kind of strange because when you come back to...
I think that it narrowly avoided the mathematical theory.
I think it's imaginable that it could have gone down that path.
So, at the turn of the 20th century, biology was deeply mathematical and statistical. And so there was the Pearson and the biometricians, and that were mixed up deeply with the eugenicists, who were kind of like, there's a statistical outcome for heredity.
Right.
And we don't really need to know what the hell is down there. It seems like a lot of effort. We can basically just look at populations. We can predict what's going to come out and, cull the crosses that we don't like and just work within that framework. And I think that the only reason that we figured out that there was something down there is because we had microscopes. because people actually could look through the microscope and they're like, hey, there's a unit and it does stuff and it seems to change and there's transformations inside of it. And some guy went and collected white blood cells from like used bandages at hospitals and scraped the pus to get the nucleus and then identified that it was this phosphorus heavy molecule. And instead of becoming mathematical, there was enough biochemistry and enough microscopy that people could actually say, well, there's more than just the math. And it could have gone mathematical.
Well, it could have gone to the point where it was just, it's only statistics, never ask more.
Exactly.
Which is, some people looking at from the outside, quantum mechanics, for example, could say that looks like it's just statistics, never ask more type thing.
But you don't think that that's what it is?
I don't think that's how it works. And but that's in biology, just to talk about biology for a moment, biology has had two big theories: natural selection and the digital nature of DNA. Those are its two big, I would say the two big guiding theories. And maybe the fact that things are molecular, things are biochemical underneath. I think there's more actually that can be made theoretical in biology. And in fact, I've been putting some effort into doing that. One of the things about biology is that biology, the big thick biology textbooks are stories of computational irreducibility. And they're kind of almost embarrassingly so. Last year, I happened to finish something I started in the mid-'80s and couldn't make work in the mid-'80s, which was to make really a minimal model for biological evolution. What is it actually doing? When you look at kind of very simple systems where, the phenotype is so sort of trivial, you can sort of see every bit about what's happening. And it turns out you can kind of understand the way in which evolution can kind of have different ideas about how to achieve some objective. And you can see how it has what those ideas are. And those ideas are basically these different lumps of irreducible computation, which happen to be able to be fitted together to achieve some fitness goal. And there are many different possible paths it could have taken, but the one it actually took, which succeeded in achieving that fitness goal, is just some collection of sort of the random sort of rocks of computational irreducibility that happen to fit together in such a way to achieve some particular fitness goal. So when you say, why is biology the way it is? Why? The answer is because it got this particular random lump of computational irreducibility. And now when you look at the textbooks and they're describing this endless detail of, this molecule does this, it's kind of like, oh my gosh, this is, I can look at these things that I can run, little programs and things, where I found these kind of computationally irreducible sort of lumps of functionality. And it's just like these biology textbooks. These biology textbooks are describing the kind of entrails of this computationally irreducible thing.
Okay, so what about abstraction layers? Because if you look at something that is computationally irreducible, is there some way to stand at a different place, get a different perspective, and somehow shift the way that you see it in a way that reveals some fundamental pattern that fits on top of the irreducibility, so it's still true?
Right. So, one of the features of computational irreducibility is in any computationally irreducible system, there will always be an infinite number of pockets of computational reducibility. So, in other words, you've got this random arrangement of bits. If the thing was really perfectly random, you could, for example, immediately say, it's 50% black, 50% white, for example, which is already a reduction, so to speak. And it turns out in any computationally irreducible system, there are always an infinite number of little pieces of reducibility. So things you can say. And so that's kind of a, for example, both science and for technology, that's an interesting thing because it tells you you're never going to run out of scientific laws you can discover. They may not be, you're never going to run out of inventions you can make. There'll always be another little piece of reducibility that you can make use of. So what happens, for example, in physics is our experience of the universe is sort of looking at certain slices of reducibility. So the fact that, take the gas molecules, for example, we could be really having our noses rubbed in the details of those molecular motions. And we would be like, this is very confusing. But the fact is, we operate at the level of this kind of slice of what's happening, where we're just talking about temperature and pressure and velocity of gases and things like this. And so we're able to kind of glide through this kind of this pocket of reducibility. And this is a feature of us as observers of what's going on, that what's really going on is there's all this irreducibility, but we are merely sampling some piece of it. For many purposes, we're merely sampling some piece of it that is reducible, and where we can make simple statements like Newton's laws, for example. Biology is not sampling the reducible stuff. The biology textbook is in-your-face irreducibility, so to speak.
Okay, so this is why I really like Michael Levin's work, because I think that in some way his model of desire is that next frame of being able to take something that's computationally irreducible and to say, well, you can see what it will do on the basis of what it wants.
I don't know what wants means.
Well, you have desires, don't you? Like, you go and I saw you eating a sandwich earlier. Why'd you pick that sandwich?
Yeah. I mean, whenever you have a system, you can describe it in terms of its mechanism, or you can describe it in terms of its purposes.
Sure.
So, for example, my brain, you could have measured all kinds of neuron firings in my brain and decided to, there is a mechanistic reason why I'm going to eat that piece of chocolate or whatever. Alternatively, you could say, I've got a better description. I'm going to say he wants to eat the piece of chocolate. Okay? So there's a trade-off between these things. And sometimes the explanation by mechanism is a simpler explanation. Sometimes the explanation by purpose is a simpler mechanism. It is a little hard to, I've actually been slowly understanding this recently, the kind of the theory of purpose. So you can have, what's interesting about mechanism is you can describe it in terms of rules. Purpose, usually you have not been able to describe in a similar way. So it turns out in my sort of day job in life of building our computational language, Wolfram language, which is sort of an attempt to have a computational representation of everything in the world, one of the things that we would like to represent is things about the things that humans normally talk about. And so that gives us then a kind of a symbolic representation of the I want to eat the piece of chocolate or whatever else. And we start to be able to have something where you can merge what is, for mechanism, we've had a good sort of rule-based way of describing mechanism. We have not generally had a good rule-based way of describing purpose. In other words, you say, these are the goals for your program. Well, people often will just sort of write those down as a spec sheet or something. But they would say, well, if I were to write those down in explicitly what they are, I would have written the program. But actually, it's not quite the same way. I mean, you can have something which is a description of what the purpose should be that is distinct from the description of the mechanism, how you get there. And so there's an interesting trade-off of sort of, for example, could you describe the laws of physics in terms of purpose? In traditional mechanics, there is a way of formulating them. I mean, Newton's laws say there's this force, there's this acceleration, and so on. Lagrangian mechanics, the principle of least action, for example, says the motion will be such that this quantity called the action is minimized by the motion that happens. So it's an explanation by purpose as opposed to an explanation by mechanism. Those two things are mathematically equivalent in that case. We know how that equivalence works. In computation, you can also make an equivalence. It's a little trickier, and it relates, for example, to the famous P versus NP problem in computational complexity theory, is related to kind of the problems that are polynomial time problems. You just grind through it. You can work out, multiply two numbers. It's just you know what to do with the next digit. If you're asked to factor a number, say this number is actually the product of these two other numbers, it's like, well, how do you find the numbers that are its factors? Well, you might say you have to just try all the possibilities, whatever, but you can state the objective. I want to have numbers which, when multiplied together, make this first number. You can state that objective easily enough. And now the question is, but that can be stated in a computational way. What is not obvious is that it takes the same effort to satisfy that as it does to sort of grind through things by mechanism, so to speak. But I mean, the big point I would say is that describing biology in terms of purposes, I don't know if that makes any sense. Okay, so
it seems like that's kind of what the ancient pagan religions were attempting to do. I think that's a sort of charitable interpretation of what the ancients were trying to do, was to group together purposes that are all playing out inside of people's daily lives into these archetypical stories that they could represent, and so that people could behold them and discuss their own attachment to each one of these actors.
You mean in terms of kind of the spiritual view, the spirits for how nature is moved, so to speak?
Yeah, exactly. Like the motivating forces, let's say,
Right.
Rage, lust. Like these are some of the big ones that everyone experiences at some point in their
Right.
life, and you don't really have to be taught how to do it. It's sort of happening inside of you all along.
And so you project that onto the natural world, which is, in for us humans. And this is something very relevant in the time of AI. For us humans, we know what it feels like to be inside us, so to speak. We extrapolate that something similar must be going on inside these other critters that kind of look a bit like us. We sort of extrapolate that the things that are going on in us are just like what's going on in them. It's less obvious that the things going on inside the AI that's just sitting in your computer or whatever are the same as the kinds of things that are going on in us. And similarly,
doesn't that line become really blurred if you take an AI and you embody it and you give it full connection to the senses and the ability to go out into the worlds and collect data and make more of itself and then educate the version of itself that it just built in the laboratory to like go out and do the next thing? Like as soon as you have that, haven't you created a self that's walking around that has interiority that is at the very least some fractional representation of what we have?
Sure. I think your computer probably has feelings about itself, so to speak.
Do you really?
Yes, I think if you think about what it's like to be a computer, okay, I think I know what it's like to be me. I can guess what it's like to be another person because I kind of extrapolate directly from me. Can I guess what it's like to be a computer? It's what's the life of a computer? The life of a computer is mostly from when it's booted up to when it crashes. That's its lifespan.
Restart more frequently than that.
What's that?
I said you're supposed to restart more frequently than that.
Maybe so, but that's that's almost the. It's not quite eugenics, but it's some kind of euthanasia of computers. It's kind of this is what biology discovered, the same thing that we discovered with computer operating systems, which is, it's often much, you can't fix them, you just have to restart them. And that's what biology does, in successive generations. It's like, any given generation gets certain traumatic things that happen to it or whatever, and it will eventually, it fails. And so you just start another one, just like we do when you run a computer.
But I feel like internal experience is inexorably tied to this process of generation. And so if the computer's not going to make another computer, I don't know if there's any reason to believe that it would have experience, because this is, I think, where desire and will comes from. I think it's literally the process of this need to reproduce, or the push to reproduce.
How do you feel about mules?
Sad, mostly.
Okay. I'm gonna start asking whether you guys have kids, because that sounds like it is a.
No, but we don't have kids, but it's a latent capacity, right? Like the cells inside of the being are reproducing. I think that a being is an agglomeration of the human cells inside of it, the bacterial cells inside of it, my relationship to the person who's sitting next to me, my relationship to history, my relationship to the future, my sense of what is good, my sense of what is bad. Like all of these things combine to offer purpose. And I think that there is this inherent sense of being able to look that provides for that. And without being able to look, then how does the computer have experience?
Your computer has a camera, I suspect. It's looking at us right now, but no, at a more, in terms of what, if you are going to define humanity as, in the end, the only things that are just like humans are humans. And you can say, well, the embodied AI, it's getting really close to being a human, but no, it's not really the same because it doesn't reproduce itself. It's not the same because it doesn't have mortality in the same way. It's not the same because some detail. And yes, the only thing that will satisfy all those details is us humans. And so you have to decide, what's the generalization? What are you prepared to generalize? And I think that, this notion of inner experience, which people sometimes attribute, that's the magic thing we humans have that nothing else has, is, I think that's I don't think that's really right. I think one of the things this piece I was just writing about bigger brains, I thought, how am I going to illustrate this? Well, the thing opens with a picture of my brain. And it is funny, as you look at, you look at some MRI of a brain and you're like, you can see the stuff that's there. I've never done fMRI. Those are rather tiresomely long to do, but and they're not quite as, you can see what you're thinking immediately type thing. But it's still, there's a certain sense of, look, it's right there. It's just these nerves, a bunch of neurons and so on. It's not. It's an interesting thing to kind of get used to the idea that your internal, that you can see. In this MRI, you can see the thing that you are inside of having the experience that you're having. And that's a thing that you say, well, I can, open up my computer, I can see its CPU chip and so on, and I can kind of see what's having that experience. But it doesn't, and you might say, well, it's just a CPU chip. Well, it's just a brain too. I mean, I think this whole question of whether, what it means to have an inner experience is I think at some level it's sort of disappointing, because at some level there's sort of nothing there. It's just like, well, of course it has an inner experience. To the outside world, it is doing the things that it would have if it had an inner experience. Is the description of it as having an inner experience, is that a good description of it that it could sort of tell itself? Well, sure it is. It's fine. It's just like, I imagine that you have an inner experience, but can I prove that? Absolutely not. I can't. I can no more prove that you have an inner experience. I can reasonably extrapolate based on my impression of an inner experience that you're similar enough to me that you're probably having the same kind of a thing. Right now, if I were just having a conversation with you through a text chat or something, I think it'd be very unclear whether, the thing at the other end of that is it having an inner experience or not? I think it's, I don't think that's a meaningful distinction.
Hey guys, quick interruption. Remember, this program is entirely paid for by you guys. That means we work directly for you. We got those sponsors. We're not trying to sell anything that we didn't make. But we need you to come over to patreon.com and see if you can make sure that we can continue to do this and continue to do it even better. It could cost you as little as 75 cents a week, so that's probably nothing, but it adds up to the point that we can spend all of our time doing this. Anyways, I'll see you over at patreon.com/DemystifySci. Enjoy the rest of the conversation.
Well, so with the question of purpose, I think that bordering experience on what humans have is the thing that creates the problem. Because I studied bacteria when I was in grad school, and they seem to operate by a really simple rule. They want to be comfortable. They want to decrease their redox stress. And as soon as their redox stress goes out of bounds, they activate all of the programs that they need to activate in order to change their environment or change where they are in order to be more stable. And I think that that's kind of the simple rule of biology that everything fulfills, which is that there's some internal set of sensors that tell you what feels good, and then you interact with the world in such a way that it maximizes your feeling of feeling okay. And everything does that. And we put, as humans, we put very complex structures on what that is, right? We have careers and we have callings and we have these questions of meaning and everything else. But I think that fundamentally it's just this progressive complexifying of a simple principle.
Which is different, you think, from principles in physics like energy minimization?
I think so, because it's an experiential process, right? There is some aspect of physics in that, which is that that I'm sure that energy minimization has to be involved, because fundamentally redox stress often comes from metabolic processes. And so you're trying to balance the effects of whatever is influencing your metabolism. But you
don't feel that that's the only thing that's going on. You feel there's more to it.
I do feel.
See, I think that's in some sense, this question of whether, okay, so first point is, there is, you might ask, and it's very relevant for AIs, is there an ultimate purpose, right? It's been relevant in theology too, but it's relevant today for AIs. Like, we build the fanciest AI. Is its purpose going to be to eat us all and, make paperclips or whatever the myth is around that? The thing to understand is there is no absolute purpose. Things, and that's, what human purposes end up being are dependent on our biology, our cultural history, our experiences, et cetera, et cetera, et cetera. It's a very, complicated mess of things, and it's, changed over the course of human history and so on. And I don't think that, if we say, so for example, for the AIs, people say, well, we're building these AIs and we're building them and they're going to be much fancier than us humans. And then what's their purpose going to be? Well, they won't have an intrinsic purpose. If we imprinted on them a purpose, like the history of biology of life on Earth has imprinted the struggle for survival on all life on Earth, because that's how it's worked, so to speak. But unless we imprint that kind of thing on the AIs, the computational processes in the AI don't have an intrinsic notion of purpose. And so I think it's just like, so a question would be, does nature have purposes? I don't know. I think that's a question that you can say, this, you might anthropomorphically describe some natural process as, that stream is trying to make itself have a simpler path down to the ocean type thing. That's from the outside, that's your view of what's going on. And you mentioned the ancients, so to speak, or the animists and so on, who say the reason that the moon does that is because, and then there's some human-like story, right? And I think that's an assignment of purpose, so to speak, because that is the way that we think about what we do. We don't think about what we do so much in terms of mechanism. We don't think about what we do. It's like, I'm feeling hungry, which is sort of a purpose type statement, rather than, whatever it is, the pH level of my whatever has reached this, which would be a much more mechanism type thing. That's our narrative that we find for describing the world is more conveniently in terms of purpose, even though there is underneath some perfectly, some mechanism there. And when it comes to the ancient descriptions of science, purpose was an easier thing to reach for than mechanism. Mechanism came much later. And I think that and then mechanism kind of a little bit fell by the wayside in the mathematical period of science, because it was just solve the equation. And then the idea that there would be any kind of thing where you could understand it by step by step by step, you could do the natural philosophy, you could do the kind of reasoning through what the universe was going to do. Now natural philosophy, I think, could distinguish itself from kind of theistic explanations of things, which is, natural philosophy is you can reason it based on its mechanism. Theistic explanations tend to be, it felt like doing that type thing for whatever, human, projected human kind of reason.
Well, I see it as the ancients actually trying to work out their own internal states and how they were going to live with often contradictory internal states among one another in these complex societies. That I think it was just a sort of public project to work these things out, perhaps. Like, you tell a story about the sky, not really because you care much about how the sky works per se, but it's a great opportunity to reflect upon how each one of us works in the larger concert of our society. So it was perhaps just a completely different project than science itself.
And it's hard for me to look at human society and not see that there's a very, very important mythological component, even for building something like AI. Like we were talking earlier about the crazy projects that are going on in San Francisco, the company that's trying to build this tabletop semiconductor. And there's this kid who's at the heart of it. I mean, kid, he's like a 25-year-old man. But we went and we talked to him, and it was...
He has the enthusiasm of a kid.
Yeah, and just completely wide-eyed.
Can we just give Sam a shout-out?
Yeah, Sam Zalip.
Sam's going to do this show eventually. He promised he would. But yeah, Sam Zalip, right?
Yeah, but he's like, it's crazy because we don't have a myth that tells us what we should be building. And I wonder if that isn't something that is completely unable to be provided by with Mechanism alone. And I'm like, if you're trying to talk about purpose, you can break it down to Mechanism of there's pH changes in your stomach, but then there's a spiritual question of what will you eat? Will you be vegan? Will you be vegetarian? Will you eat free-range cattle? Will you go hunting? Like, there's some aspect of this choice that seems like it's not just purely Mechanism, it's also an aspirational thing. And I also start to see this...
Because you're planning a future, right?
You're planning a future, and I feel like humans to an enormous extent have a sense of future.
And you vote on the future and the choices you make with these things, I suppose.
And I have a feeling that there's also this speciation event that can happen, which I see the axis as being between the bioconservatives or the bioconservationists and the transhumanists. Because there's people who will continue to live on the land, and they will continue to farm, and they will continue to fish, and they will live that life. And then there are the people that are going to merge with the machine. And it's hard for me to imagine that 10 million years from now, they'll both still be Homo sapiens. They will be two different groups. And so what now can we observe in their tendencies that leads to that eventual separation? And it's taste, it's preference, it's culture. Like, how are those things not mythological in nature? Because we see who we want to become, and we aim for that in a way that is underpinned by Mechanism, but not fully described by.
Yeah, I think the living of human lives is something that works well with purpose. It's, the living of human lives by pure scientific mechanism is not a human life that people are excited about, or most people are excited about. It has been a feature of modern times that as we've more science-ified thinking about human life, these kinds of purposes that have been previously identified, like, do it for the greater glory of God type thing, whatever that might mean, is, those purposes fell by the wayside. And that led to, the whole sort of self-help type, it's all, which is a more, I would say, if you were to read that on this axis of purpose versus mechanism, it's much more on there's only mechanism. This is not, there is no higher purpose, so to speak. And people do much better as a practical matter when they feel that there is some purpose. I mean, it's an interesting question. If there's effective human immortality, how will that affect the perception of purpose? Not clear. It's kind of like, some part of, and you mentioned sort of reproduction of humans, so to speak. It's like, is that, to what extent is that working its way backwards into lots of things that humans do? I think, these are, and by the way, a lot of the things we're even talking about, if there was only one of us, only one human in the universe, so to speak, many of the things we might talk about science, about narratives, and so on, they're all irrelevant. I mean, the fact that there are many minds that are somehow aligned, and where we have these things like language that allow us to kind of get that alignment between minds is important. I mean, we wouldn't, the notion of objective reality is pretty weird if there's only one of us. In other words, objective reality is this collective agreement about what happened between these, fairly similar minds who are aligned by their common description of things that they align through language and so on, and that they've kind of intrinsically got alignment by their common biology and so on. So I think it's a strange thing when we imagine, maybe we'll talk about this in a bit, the sort of this thing we call the Ruliad, which is this sort of ultimate thing that is the sort of thing underneath all reality, so to speak. And the fact that we have a view of what's going on in it that is based on us as elements inside the Ruliad, And the fact that we all sort of believe in an objective reality, I think, is because we're all really pretty similar and we're all pretty close by in real space. In other words, it's kind of the way I would think about it is, we take, the night sky. We're all on this one planet. And so we all pretty much agree what the night sky looks like. It's not because the night sky has to be that way. We could be on another planet somewhere completely different. We don't have a way to say abstractly what should the night sky be like, because we happen to be on this planet that it is the way it is. But the important thing is there's 8 billion of us on this planet, and we all kind of are seeing the same thing. We're nearby and we're seeing the same, and so we're seeing the same thing. So we all agree about this thing that we can call an objective reality, so to speak.
And so my instinct about that is that our ability to parse the informational content of non-human brains really shortens our horizon for what objective reality is. Like, if we could talk to whales, if we could talk to trees, if we could talk to birds, I think that we would have a really radically different understanding of what reality actually looks like that might get us closer. And I don't buy for a second that these creatures don't have an internal model of reality. I look at my cat, she has a model of reality. It might be limited. It might be...
She thinks the same about you, I'm sure.
I'm sure she does, yeah. But there is something there that I know that she goes out and she notices things that I don't.
Do you think the weather has a view of reality? Even though people would say quite often the weather has a mind of its own, because the weather seems like it's operating according to free will.
Well, it's not I think that being alive is required for having an internal view of reality.
That's an interesting claim.
Yeah.
That's a very interesting claim. I think this question of what it means to be alive is also a complicated question. I feel like I'm getting closer to having an understanding of that. And the thing that is I think there's a thing that's sort of been missing in science, which maybe I'll be able to figure out. I just had an idea a couple of days ago that is sort of a beginnings of something. And the question is really this. If you're looking at a biological organism and you say, okay, inside the cells, there's all this cytoplasm and so on. What is it? What kind of state of matter is it? Is it a solid? Is it a liquid? It's really neither of those things. It is a thing where increasingly we've learned from molecular biology, every motion of a larger molecule is orchestrated in some way. I mean, we might have just thought the muscles are getting tighter. Well, no, they have these little things walking down them that do what they do. And, it's a bulk orchestrated kind of dance of molecules. And there's this kind of notion of bulk orchestration. We also see in technological systems, in microprocessors, let's say, operating systems, whatever, there are things where there is this orchestrated set of things going on. And it's not just we don't think of what's in a microprocessor as being like an electron gas. It is something where there are these particular things going on, but we would like to describe that in bulk. And it's kind of like in statistical mechanics and things like the second law of thermodynamics, we just say, we can describe the molecules as being kind of random in what they do. So I have the beginnings of an idea for how to think about sort of a bulk orchestration kind of system where the system isn't just doing random stuff, it's doing stuff that is somehow orchestrated. Now, you might say, how does that relate to sort of ascriptions of purpose to things and so on? That's an interesting question. I don't know the answer yet. That's why, I mentioned that I've been thinking about things like how do you characterize purpose in the same language as you characterize mechanism? And you need that if you're going to have something where you can have a description of sort of things by purpose versus things by mechanism. But to mention one thing, I was mentioning biology, I think, is a story of kind of lumps of computational irreducibility. One of the things that's kind of interesting is so actually it's very bizarrely similar to the second law of thermodynamics, something I realized only quite recently. The question of why biological evolution works is bizarrely similar to why the second law holds. And so the second law holds because we make only these computationally bounded observations. We can only make those kinds of measurements and so on. But underneath, there's also all this computational irreducibility. Okay, so in biological evolution, there are all these computationally irreducible processes which make all these, which as you mutate the genome or whatever, will make all these complicated things happen. But I think the forces of natural selection tend to be computationally bounded. That is, what's happening is the forces of natural selection make that beak get longer, that one gets shorter. They're very coarse relative to all of the kind of computational details of what's happening underneath. If biological evolution said, no, I want this incredibly specific, arrangement of molecules in the beak of the finch or whatever, then that will be a tough thing to achieve. But the very fact that biological evolution asks for these coarse kinds of things, its fitness functions are coarse. That's why it works. And it's the same reason, the second law is working, because we humans have only these very coarse ways in which we kind of analyze the world. And so if you required biology to have, if the fitness function in biology were as elaborate as some of the, it had some very elaborate form, it would not be possible for evolution to get there, I think. And so it's the fact that it can get there and successfully gets there is, even though when we look at how it got there, it looks really complicated. It's like, this is an amazing achievement that it got there. Well, that complexity is coming from computational irreducibility. There would be many paths that would get there. They would also look complicated. The fact that it is possible to get there is a consequence of the fact that the where you're getting to is a computationally bounded destination, so to speak.
That almost seems to imply that if life can only occur on Earth-like planets, that there should be human beings at some point on all of these planets, that they would converge. It's a very convergent model, it seems like.
Well, that's an interesting question. I mean, I think one of the things about sort of this whole SETI business of, this idea that it's a lack of imagination to believe that the only way you can get things that are like us is to have, liquid water and this and that and the other thing. I mean, I think that the sort of the test case is, imagine you've got these radio signals coming to us and they have this detailed structure. And, and then you say, well, the radio signals that come from us have this detailed structure because we designed our cell phone, protocols this and that way. The things that come from the pulsar are coming that way because it's a rotating neutron star and it's, producing a pulse every so often. But then when you look at the details of its magnetosphere, it's got all these elaborate, complicated things going on that, there's this question of, can we distinguish those complicated things going on from what is going on this planet, so to speak? Is there a fundamental difference between those types of things? A nice story about this is back in the 100 years, a little bit more than 100 years ago now, when radio was a new thing, and I think Tesla was big on this, was, listening to radio when there weren't any radio stations around. What do you hear? Well, you hear the Whistler modes of the ionosphere, and they have this woo type sound. Okay, many, many years later, people discovered whale songs. They sound remarkably similar. And now the question is, what do you conclude from that? Do you conclude that the ionosphere has a mind-like activity going on, or do you not? Because you say, well, the ionosphere doesn't seem to have, it's not alive in the same sense. The whale, even though it's making, very similar noises, it's, it's more like us. We can kind of see ourselves in it. And so I
think that's a question that might be answered soon, actually. So we have a friend who's a linguistics professor at Berkeley who's working on actually using AI to decode.
Yes, I know these projects. Right.
So
it'll be great if it works.
Maybe he'll work on the ionosphere next, is what I'm hoping. I'm going to go, hey, Begush, let's point our minds at this.
Yeah, right. Well, no, but I think that there's always this question of, what is the world model of the cat, the whale, whatever else? And, our world model is deeply based on the particular sensor inputs that we get. Dogs, for example, it's mostly olfactory. Their models of the world will be somewhat different. It's worth realizing that our model of the world is pretty dependent on the details of how we are. So, for example, even the notion of space depends on the way we are. So to give an example, look around the room. It's, 10 meters away to, the other side of the room or whatever. And light comes to us from 10 meters away in a microsecond less, 10 nanoseconds, whatever it is, right? It takes our brains milliseconds to process that. So for us, It's like there's an instantaneous state of space. Everywhere, we just see this sequence of movie frames of the way the world is. Now imagine our brains weren't made of biological stuff, but were digital electronics. It's 1,000,000 times faster. And so it's no longer the case that we aggregate all of the photons that are coming in from the things around the room. Then the idea, somebody would come along and say, I've invented this idea of space. And people would say, what the heck is that? I'm just seeing all these photons coming in. I've got this whole model of the world that's based on correlations between photons and so on. What do you mean? There's this overarching thing you're calling space. It's that feature is a consequence of an aspect of the way we are as observers. My guess is that the model of the world, that a critter where olfaction is the big source of data, be bizarrely different from ours. Even the case of the whale, for example, for a whale, I don't know to what extent whales would have the notion of discrete objects. When do they have a discrete object? The stuff they eat isn't discrete objects to them?
I suppose mating?
Maybe, yes.
Socializing.
Okay, there's one more whale. Right, okay, so there's one whale. All right, so that's
whalers, perhaps.
What's that?
Whalers.
Yeah,
harpoons.
right. Maybe. I think that even that's not. I agree with you that the my mate, the other whale type thing might be a notion of one version of a discrete object. But for many things that whales do, the notion of discrete object, which seems so incredibly obvious to us, I don't think is as obvious. I mean, if the only discrete object they run across is another whale.
What about like giant squid? They pull whales out all the time that have these crazy tentacle scars on them.
Yeah, okay, fine.
Well, they must negotiate like the bottom of the ocean and
yeah, but that's a continuous thing. I see it. It's hard to know. I mean, it's hard to put. We're talking about what it's like to be a computer, for example. What it's like to be a whale. I think we probably have more knowledge of maybe more knowledge of what it's like to be a computer than we really have of what it's like to be. Well, what it's like to be a microorganism, for example. That would be that's potentially quite challenging to. But in terms of what the world model is and what does it even mean to have a world model?
Well, and I think that the frame of reference for the way that we encounter concepts, I get what you're saying, and I think that it is very, very important and a very deep point, which is that even if we were able to find that there are syllables in whale song that contain some kind of information, and that information appears to be language-like, the question of decoding the language and being able to figure out, like, what is the whale saying about its experience in a way that maps onto our experience seems almost insurmountably difficult because of exactly what you're saying. The way that we encounter the world is so radically different that how could you possibly... There's no Rosetta Stone where there's somebody who's been both a whale and a human and is like, hey, I happen to have written out this text in whale, human, and whatever interim, and now we have some decoder ring. That's not possible.
Well, I mean, the fact is that we have, similar neurotransmitters, as Darwin was fond of pointing out, the facial expressions of, the dogs are similar to the humans, so to speak. So these emotional connections are some kind of Rosetta Stone, and some of these.
But I doubt that he would have said the same thing about the whale. Do you know what I mean? Like, does the whale have similar facial expressions to the human? It might not.
I don't know.
Right?
I'm not sure that they will have been well recorded. I mean, it's that's one of those things that's kind of tough to, they're putting these transmitters on the backs of whales for a few days to say where the whale went. But I don't think there's a face cam for the whale. But no, I think
it's a job for Palantir, I suppose.
But anyway, I think this question of what are different views of the world? What is the world like not to us? Very interesting question. I've spent lots of effort trying to think about that. It's a hard thing to wrap one's brain around. I mean, a few things one can say. So, for example, generative AI gives one an interesting perspective on that. You take an image generation AI system and you say, make me a picture of a cat. Okay. It's going to make this thing that is, it's a picture of a cat, make a picture of a dog. Okay, take the internal kind of embedding vectors inside the neural net and interpolate between the cat and dog. It will make something which continuously goes from cat to dog. If you just look at the space of possible internal ideas about pictures inside the generative AI, you'll find, for example, there's a cat island. There's a region of those internal parameters that makes things that look like cats. There's another one that makes things that look like dogs. But in between those, there's what I've been calling interconcept space, where, you're in a place where we don't yet have a human concept for that. It's not obvious we won't ever have one. I mean, I've been interested. I wrote something about this last year, and there have been now several art exhibits that have used pieces of, my stuff from interconcept space, so to speak. So, the sort of the bizarre thing that could happen is somebody could say, that's kind of a style of art that corresponds to that place in interconcept space. And that then becomes a word. There'll be some weird word for it that represents that. And then it isn't an interconcept space anymore. It is a concept. We have a word for it. But I think this gives us some sense of kind of what's out there in the space of concepts that could be, that aren't ones that the history of our civilization has identified as important. And it is shockingly small. The region of space that is not interconcept space, the region that's the planets as opposed to interplanetary space, so to speak, or interstellar space or whatever, is remarkably small. I mean, even in some simple model, it's like 1 part in 10 to the 600 is the non-interconcept space. So the vast majority of what could be is not things that we have named with the 50,000 words we have in typical languages. We never named those things. And
do you think we forget some of them?
Over time?
Yeah.
That's an interesting question. I mean, so if you look at some ancient art, there's one particular thing from Syria, I think, which is the set of black and white squares. Okay, I think it's from 7,000 years ago, maybe. It's surprisingly old. And it's like, what the heck is this? And nobody knows. And it's like, that was probably a thing to somebody, or these things in caves where there are a bunch of handprints. What were those handprints doing there? Was it a bunch of people who were like recording the fact that they were getting together? Was it somebody testing out their new painting scheme? We have no idea.
Maybe they were acting out some drama too that's been lost to time.
Well, indeed. Right. But I mean, I think that yes, I think that it is an interesting thing that, even across archaeological time, it is very difficult for us to know what was going on. I mean, you talk about purpose. One of my favorite experiences with respect to purpose was I was visiting some archaeological site in Peru, and a bunch of stones there and so on. And it's actually a very isolated site, but somebody was kind of showing us around. And I was saying, what's that? Oh, that was for ceremonial purposes. 90% of what... Right, 90% of what was there was for, quote, ceremonial purposes. What does that mean? It means we don't have the slightest idea anymore what it was for. And it's like when people say, I've heard the claim that, anthropologists claim, although I have to admit that none I've actually talked to have made this specific claim, but it's sometimes claimed that, there are societies that have been kind of just hanging out for 1,000 years. And it's like, what do they do when they just hang out, when they no longer have, when they're no longer sort of forced to do things and, have all kinds of pressure to do this or that? What do? Well, people say, well, they do very ritualistic things. And it's kind of like, well, yeah, so do we at some level. I mean, looked at from the outside, a lot of what we do is sort of ritualistic because you don't know the inner, we feel we have an inner purpose for doing this or that thing. But, doing podcasts is at some level deeply ritualistic from the point of view of, I remember, I'm reminded for some reason of a years ago when I was working with some corporate lawyer, okay? And smart guy. But anyway, I'm talking about, things that I'm interested in doing. And it's like, well, one day, I'm interested in working on fundamental theory of physics. Looks at me and says, why on earth would you do that? It's like it's a different worldview of even in a sort of pretty close together, cultural niche.
That was actually the opening question I had in mind, but Nasti beat me to the punch. I am curious why in the world you would choose to work on fundamental physics, but we could get back to that, I suppose.
I can answer that question. I mean, well, it has a personal history to it, right? So when I was a kid, I was interested in the future, and space was, in the 1960s, space was the future. And it wasn't for 50 years after that, but that's, so I got interested in those kinds of things. And then I was like, well, how do you design spacecraft and so on? That got me interested in physics. And then that was kind of, and then actually we mentioned the second law of thermodynamics early on. And one of my sort of formative experiences was I got some book about statistical mechanics when I was 12 years old. I used to be much more organized. I used to write the date when I got each book in the book. So I know it was June of 1972. So and this book has this picture of this, molecular sort of degradation to randomness of molecules. Many, many years later, I discovered the book cover is kind of a fake. But again, that's another sort of footnote to the
It was real for you.
Yes, right. But the thing was that what was really interesting to me about that book, I realized many years afterwards, is that book kind of described how a major law of physics, the second law, might be not just a thing that happens to be true, but a thing you could derive that would have to be true. So this
From some first principles.
Yes, which is no other, the books about electricity and magnetism, the books about, mechanics or whatever, they weren't making any claim like that. So that was an early formative experience. Then
what was the book called?
It's called Statistical Physics. It's part of the Berkeley Physics undergraduate physics course series. It's but anyway, then I it happened that particle physics was having sort of a golden age in the 1970s, mid 1970s, and so as the teenage me was really into that, and I would say all the different kinds of particles were my personal friends. These little books of particle properties I used to have one of these. I carried it around. I just recently got the new version of it, which I hadn't had for years. And it's really disappointing because it used to be so thin and you could actually, there were a small number of elementary particles. Now it's a big, thick book full of all kinds of stuff that is clearly not very elementary. So, but in any case, I was interested in particle physics and also cosmology. And it was a time when you could make progress. And so, the 16, 17-year-old me made real progress in those areas. And that was kind of cool. And that was, it was, that's a positive feedback loop, so to speak. And it's...
Wikipedia says that you got your PhD at the age of 20. Is that true?
Yeah.
How did that happen? Like, that seems young.
Yeah, it's young.
You beat us by a decade somehow.
Well, let's see what happened. I got interested in physics. I learned a bunch of physics from reading textbooks. I started writing physics papers when I was 15 or so. Then I kind of sort of went to college, but that didn't last very long. And so then I went to graduate school. And then I could easily have gotten my PhD while I was still a teenager, but I didn't at the time. That, future Wikipedia statement wasn't on my mind.
Was it just that you didn't have to finish a 4-year college degree before going to graduate school?
Yeah, kind of. I suppose. I don't know. I don't think. Look, I didn't finish high school. I didn't finish college. I'd written a bunch of physics papers. I went to graduate school. Then I was at Caltech, and they wanted to hire me as a professor type, and so then I have to have a PhD. So that's kind of how sort of how that happened. But then in terms of my personal trajectory, so to speak, I had discovered this kind of secret weapon, which was you could use computers to figure out things in physics. Why other people weren't doing this, I have no idea. It's been one of the mysteries of my life, so to speak, is that I try and use tools, I build tools and so on. I suppose it's the meta problem of the marketing of things I've done that, I build this stuff and lots of people use it. So I'm not, there's no complaint there. It's just that a lot of people who should be using it should be using these tools don't use them. And that was, back in the day when I was a kid, it was like, I was using all these things for doing algebra by computer and so on, and other people just weren't doing that at all. Like I was the unique character who was doing sort of frontline physics and using these tools, and it was a great secret weapon because, you would get these, it was kind of, in those days, it was kind of amusing because I'd write these papers with all these elaborate formulas in them. And people in those days, there was no web or anything. So people wanted to know, how did you get equation 11 from equation 10? It's like, well, I used a computer, and it's like that seemed completely mysterious. Anyway, so I was doing that, and I sort of ran out of the existing tools. And so back in 1979, right when I got my PhD, actually, I kind of started on the kind of building my own set of tools for doing computational kinds of things in physics and beyond. And that took me a little while. And it was, I built my first company based on that and things like this. But then I went back to doing basic science. And my big question was sort of, how do complicated things come to happen in the world? And that's what kind of got me into thinking about sort of things beyond mathematical equations, because I tried using mathematical equations to answer that question. It didn't work. So I was like, okay, what do I do? How do I go underneath mathematical equations? One of the things about building computer systems is it's a very foundational kind of activity. That is, you are trying to figure out what are the underlying primitives, and you get to invent them. And then you build up from those. And it's sort of it's the other way around from natural science. In natural science, the thing is, you're shown the world as it is, and you're asked, how does it work inside? Whereas in building up computer systems, it's like you invent these primitives, and then you build up from there, so to speak. So it's sort of the other way around. And that's kind of what gave me the idea of what I would now call ruleology, studying simple rules and what they do. The thing that was very exciting was just studying those simple rules, knowing what happens in nature. I noticed that a lot of things that happen with these simple rules, well, actually, they're very similar to what we already know happens in nature. But I wasn't finding that out by starting from nature and trying to reverse engineer it. I was finding that out by starting to look at kind of these simple rules for their own sake and seeing what they did. So then you're asking how do I get into fundamental physics? Back when I did physics for a living, so to speak, and, I was doing particle physics and cosmology and so on. If you'd asked me, is there going to be a truly fundamental theory of physics? I probably would have said, I don't think so. And I would have said it's just going to be more and more layers of an onion, so to speak, because that had been the experience for the last few hundred years of, every time you reach a certain level of smallness, there are the quarks, maybe there are things that, that are inside the quarks and so on. And that was not, so I really didn't expect that there would be a fundamental theory of physics at that time when I was working in physics. Subsequently, when I started really understanding how simple programs, what they can do, it's very tantalizing because these simple programs can do just amazing things. And so then the obvious question was, could something like that make what physics makes? Now, one of the distracting features of that, there were a couple of distracting features. One was that it is, when people out in the world just say, I'm going to come up with a theory of physics, there are an amazing number of people who want to come up with theories of physics. It's a great thing. For the physics community hates that. But the physics community should love it because there are all these people who care about physics. And I haven't quite figured out how to thread this particular needle. But the fact is, if you look at, I get these things pretty much every day, which is amazing. Yeah. Well, so it's and the thing that is very, most of them have a very mechanical character to them. They're mostly based on high school level physics or a little bit less than that, but usually high school level physics. And, the thing that makes that not likely to work is the 20th century, which is, high school physics does not include pretty much anything that was discovered in the 20th century. And it's 20th century physics actually got a long way. And so if you zero out 20th century physics, you have a deep disadvantage. Now, there are things that the 20th century got wrong. There are things that have probably been a little bit missing the point for the last 300 years or so. But still, an awful lot got figured out in the 20th century. And so that's a big handicap. So on the one side, there's an undercurrent of people who are like, we're going to figure out the fundamental theory of physics, and it's all some very mechanical thing. Okay?
Wait, when you say mechanical, like, what do you mean? It's like...
Oh, I mean electrons as loops of wire type thing. I mean, really, something...
totally different category of these theories. Like, all of ours are theories of fundamental consciousness as emerging from quantum mechanics and shaping the creation of the universe. So
okay,
it's interesting that there's...
I get those two. But there's a fair number that are, and actually that's a more modern thing. Back in earlier years, it was much more of the, electrical engineering is the underpinning of the universe type thing. Okay.
Did you have a lot of exposure to something called the electric universe?
I've never heard of it.
We'll leave it on the table. There was like a very popular, I don't want to say alternative physics community for a while that was very focused on electricity as being the fundamental building block of everything in the universe. And it seems like perhaps they would have found you.
They probably have. I mean, it's a challenging thing because I've always, from a purely human point of view, it's just the weirdest thing because there's all this effort being put into this. It's kind of like people, at some level, it's like people writing poetry because it's like poetry is more for the writer often than for the reader. It's only rarely that poetry sort of makes the jump to be something lots of people want to read. But I think, it's a frustrating thing because I've been thinking of really pushing harder to get people who are motivated in this direction to study things like rheology, because rheology is accessible without, the problem with modern physics is that there's a big stack of stuff that is, how quantum field theory works, how general relativity works. It's kind of complicated. And if you zero that out, you're not dealing with physics as we know it, in the present day. You're dealing with something which is some kind of shadow of physics that probably doesn't have much to do with the way it actually works. And so I think, it's a thing where I've been, that's a, for me, it's both, it's a bizarrely untapped resource because it's wonderful that so many people care about fundamental physics. And it's just frustrating because one would like to be able to, and it's kind of like, and I've told people a bunch of times, I've said, if you really want to do this, you got to go learn, quantum field theory and things like this, which is a heavy lift, because it's quite mathematically sophisticated. In the end, the concepts are, I feel like at this point, I feel like I have a pretty decent intuitive understanding of these things, but that's come from knowing a bunch of fancy math and all that type of thing. It wasn't something that you get to. It's not a direct thing that you can get to, I don't think. I mean, maybe I have hopes that with the physics that I've now done, that one will have a much more direct path. Although it does go through things which are not as mathematically towered, but they are things that are very alien to human experience. So they still require some kind of abstraction that isn't necessarily everybody's cup of tea. But so anyway, back in the day, one of the things about sort of fundamental theories of physics is there's a tremendous there was a torrent of these things that were really not plausible. And then that was one thing. But anyway, early 90s, I was thinking, well, I can see that very sophisticated things can emerge from very simple rules. What could the rules for physics be like? And I started thinking about networks, graphs, things like this as the underlying structure of space. And I started working some of that out. By the late 90s, I'd worked a bunch of that out. And in that big book, New Kind of Science, that I published in 2002, one half of one chapter is about fundamental physics. And as far as I was concerned, that book is mostly about kind of the thing that has been a very successful transformation in science from a time when most models got made in terms of equations to when most models are getting made in terms of programs and rules and so on. I'm pretty happy with the title for that book, which at the time people were like, oh, you can't say that. And then, I was on a podcast recently where somebody was sort of being like, well, what is it? What is it? What is it? I guess it's, it's a new kind of science. And it's like, guess what? That's what I called the book because that's what it is. Anyway, so, I viewed the main story of the book as being about using programs as the underlying stuff to make models of things, whether those things are biological pigmentation patterns or ideas about foundations of mathematics or whatever else. But I saw physics as being a potential use case. And so I wrote something about it, and what I wrote was actually quite sensible. But I knew I hadn't gotten the full distance, so to speak. And so then book comes out, and lots of people in lots of areas of science are, excited about it, starting to use what it has. But my friends, the physicists, and I knew most of them because, well, A, I'd been in that business. I'd been sort of a leading operative in that business at one point. And B, they sort of pretty much all use the technology I built every day. So I have some connection. But my friends, the physicists, were like, we hate this. We don't need a new theory of physics. We've got string theory. We're going to solve it real soon now. And so it was kind of a funny thing for me because it was like, I'm thinking, well, I'm going to pursue this physics stuff. And I had some little group, we were looking at some things, but
it would be so useful, and everybody will just welcome this and find it so useful.
Well, yeah, right. But, it's one of these cases where the market just doesn't want it. Right. I mean, I remember one chap, Steve Weinberg is his name, who has said to me, I really hope you won't do this project. Okay?
That's wild.
Well, I said, why? He said, well, because if you do it, and you're right, which of course you won't be, you'll destroy what we've done for the last 50 years. And I said, I think you're wrong. I think the stuff that's been done is what it is. It may not be the lowest level of what you could do, but it is still perfectly, most of what's been done. And that's proved out actually more than I even thought it would prove out. That, all these things like string theory and so on are interesting mathematical structures that actually plug into the kind of theory that we have. The kind of theory we have is kind of a low-level machine code. These are things that are operating at a higher level and are perfectly valid, reasonable things. They're not answering the question, how does it work at the lowest level? But they're not signed up for that, so to speak. So it was so that was sort of the response.
We see that attitude all of the time. Actually, it's really fascinating. That's a surprisingly not unique story that we've had people tell us over the years.
I would figure somebody like you would be immune to that treatment, though. Do you know what I mean? Like, usually we get it from people that don't have, directed at people that don't necessarily have the bona fides.
Well, I think there's something very strange and defensive about the way that the culture of science has been operating in the last 100 years, which is very zero-sum. And when I go back and I read the letters from the Royal Society in the 17th and 18th centuries, 19th century, I don't see it as much. I see people being more willing to have this more anarchical entertainment of ideas. Maybe they'll take one piece and leave the rest, sort of situation. But now people feel like their whole body of their work is threatened by these integrations and modifications. And I'm not sure that I like it.
Well, what happened is science is a victim of its own success. I mean, what happened is when science was small, and you see this in emerging fields, it's entrepreneurial. Maybe you have to explain why on earth you do this stuff, but everybody's, it's a fun adventure that the only people who are doing it are people who really want to do it, because otherwise, why would you do this unpopular thing? But then, science was very successful. And science has, there are millions of scientists, and there's a big institutional structure. And with that comes a certain degree of, well, we've got to organize things. We've got to have a funding program for this. And, that becomes very tribal. And that's what's happened to science. It's what's happened to well-developed fields of science. And it's always, I myself happen to have been able to live in some backwaters of science to some extent, which is much, much pleasanter because you just get to do what you do. And maybe people care about it, maybe they don't, but you can just, play in your little pond, so to speak. And I think it's true that in these things where, science got big, science got very, yes, it has, but you also have to understand that people have invested a lot in some career, some way of thinking about things, And it is very, for them, it's like, well, I hope it doesn't work this way because, I hope it doesn't go this way because I invested 50 years in this, in this other thing I'm doing. I mean, I can, it's interesting to see that for any of us, that there are things where this is the way, if it, I've invested a lot in speaking English and learning how to write English. If the world suddenly segued to a situation where I'd have to speak some other language, I'd be like, I want to avoid that. I want to keep speaking English because that's what I've invested in, so to speak. So it's hardly a surprising human response. The idea of the scientist as the kind of impartial, arbiter of things, that idea was never really an idea. I mean, scientists are humans like anybody else. And I think it's one of the things that for me is interesting, and I've been sort of lucky in this respect, is that, I basically have done science as a hobby most of my life. And both when I was a kid and, now in sort of my ancient adult life type thing. But, and so that means at some level, it's like if it works, it's great. If it doesn't, whatever. And, the thing that I've noticed is it's a tricky thing when you do science that you have to have a prejudice about how things are going to work, or you don't even try. You have to have some hypothesis about how things are going to work. But the trick is, can you ride that hypothesis enough to ask the question, but not ride it so hard that it has to come down the way your hypothesis says it comes down? And I've seen that so many times that it looks like the chips are falling not in the way that I'm prejudiced to think they should fall. And I'm like, oh, this is terrible, this is terrible. But I've seen this so many times now. It's like my principle is just, do the science, let the chips fall where they fall. That is psychologically difficult. And the thing that's happened to me many times is the chips looked like they were falling in a direction that was just horrifying for me in terms of my prejudices. And then actually it turned out they fell in something that was much more aligned with with the way I think about things. So for example, one very big thing is sort of at some level, a lot of things I've done are deeply deconstructive of the world. That is, I'm thinking about these underlying hypergraphs and this and that and the other. It sort of crushes out the humanity of everything, or so it seems. Yet, as a person, I like people. I'm interested in people. I consider people, important in my life type thing. And so it seems very strange that one is, and I realized this is a strange thing. I'm deeply deconstructing things, and yet I have this fundamental belief in people, so to speak. And then it turned out that it didn't work the way I thought it was going to work, because it's turned out that all the things I've now understood all have to do with observers, and the observer is really a critical piece of the whole story of how science works. I didn't see that coming. I thought I was deconstructing everything. But it turns out, and my prejudice was don't deconstruct things because I believe in people, but I was just following the science of let's just deconstruct everything. And then it turns out that in the end, I realized actually, I was wrong about that being where things would land. So
Can you unpack how the observer is central?
Yeah, I mean, okay, so we didn't really talk about this yet, but so we're talking about how the universe works. So we're talking about space and there's graphs and the rewriting of these graphs. We didn't really talk about that, but the progress of time as a sort of reconstituting of these graphs and so on. So then the question is, in the end, we have this rule that says how the graphs should get rewritten. Actually, that rule can be applied in many different ways. And that it can be applied in many different ways is what leads to quantum mechanics. There isn't just a single thread of history. There are many kind of branching and merging threads of history. Okay, so then I thought, well, that's a bit strange because at some point, maybe soon, we're going to be able to say, here's this rule. This is our universe. And that's a very weird thing to be able to say, because it feels very anti-Copernican to say that. It's like, why did we get this rule and not another rule? We're very special. We got this rule. It's quite a simple rule, let's say. Why did we get this rule? Why wasn't it another one? Okay, so that had me quite confused for a while. And then I realized that what happens in quantum mechanics, there's sort of a generalization of that. That's what's happening all over, which is in quantum mechanics, what's happening is that these rules, they can be applied in many ways. But then you say, well, why is there just one possible rule? Why not apply all possible rules in all possible ways? So initially you think, so I had a prejudice against this, okay? My prejudice, in fact, I had a prejudice against the idea that, my prejudice was that, we believe in a single history. And the idea that there's this branching, merging of history, the universe can't be wasting that much computation. And even worse than that, it can't be wasting so much computation that it's running all possible computation, so to speak. That's just an unbelievable, computation is sort of a more valuable thing than that, I was thinking to myself. But in fact, as you start there, and then I thought, well, if it's doing all possible computations, how does it have any structure at all? Well, the answer is that it's a slightly tricky thing, because if you're doing a if you have some state of the universe, and there's two possible computations, you do one, you do the other, and then those lead to two different states. But those two different states can end up merging to the same state again, and that possibility leads to a structure to the whole thing. It's not just a tree of possibilities where everything goes. It's this complicated structure of branching and merging and so on. So then we have this thing which is the sort of the entangled limit of all possible computations. I call it the Roolead. And so then the question is, well, okay, there's this Roolead out there. And the Roolead is kind of a remarkable thing because it's a completely unique object. There's only one of it. There's only one thing that is the entangled limit of all possible computations. There are many ways you can describe it, but it's ultimately one thing. And not only is it one thing, it's a thing that has to exist. It's not like you get to say, well, maybe there's one of these, but maybe there isn't. It's like once you have the definition of these terms, like computation and rules and so on, necessarily this thing has to be a thing that exists in the same sense that sort of necessarily 2 + 2 = 4 if you define what 2 and 2 and plus and so on are. Okay, so we have this thing. It's a necessarily exists thing. Now the question is, how do we perceive this thing? Because if this is everything, we are part of this thing. So we are observers embedded within the Roolead. And so then the question is, how does an observer that's made of the same stuff that the rest of the Roolead is made of, because it's part of the Roolead, how does that observer perceive the rest of the Roolead, so to speak? Okay, so then you could say, well, how could I possibly say anything about that? Well, the answer is, if you make some assumptions about the observer, because we know what we're actually like. We might be different than we are, but we happen to be the way we are, right? And so you have these things like we're computationally bounded. We believe we're persistent in time. So already with the second order thermodynamics, we start to see this thing that as soon as we think we're computationally bounded, we know there's computational irreducibility underneath because that's inevitable in the Roolead. Then we immediately can say, given that we know we're computationally bounded, which we might not be, but we are, therefore we can deduce that the second order thermodynamics will be what we perceive about the universe. The very surprising thing is you can go on from that and say, well, also the way that we perceive things makes it inevitable that we will perceive general relativity, that we'll perceive relativity, we'll perceive gravity, etc., etc., etc. And the same thing seems to be true for quantum mechanics. So in other words, for observers like us, well, all we know about the observers, we could, and I suspect it's the case, that if we are more precise about what we're like as observers, if we know what scale we're at, if we know that we have, brains that work in a certain way, that knowing those facts will allow us to derive more things about the universe. So, for example, we can't derive that our universe has roughly 3 dimensions of space. We don't know why it's 3. Right? My guess is the reason it's 3 to us is because it's something to do with us. It doesn't have to be 3. We could describe what's happening in the universe and with 1 dimension of space. We could be going around, just sort of examining space with this little, like a Turing machine or something, going around just sort of with just 1 spot where things are happening. And that could be our view of what's happening in the universe. It isn't. Our view of what's happening in the universe is 3-dimensional. My guess is that sometime one will figure this out, and it will be so incredibly obvious. It'll be really embarrassing when I didn't figure it out before. But it
seems like it's fundamentally because we're embodied. Bodies have length, width, and height definitionally.
Well, So you say. I mean, it's. I don't
So
think
it
that.
seems.
I don't think there's anything about. I don't think that if we were two-dimensional, for example, or four-dimensional, I don't think you would say anything particularly different. You would say, "I'm the way I am," because given that we just descriptionally say we have, 3 dimensions, then you're sort of assuming the answer, so to speak. One would like to be able to derive the answer from something more without already assuming the answer, so to speak. So, for example, the existence of discrete objects is, I think, a clue. Okay, I'll give you another example that I realized recently. The perception that we have of the universe depends greatly on the fact that we have non-zero mass. If we were massless, like photons, we would have a very different view of the universe. And particular time, for a photon, time doesn't pass. There is no the photons that were emitted at the at recombination 100,000 years after the beginning of the universe. They, as far as they're concerned, no time has passed between that moment happening and the time when they hit some detector, in orbit around the Earth or whatever. So
they haven't sampled the state of the universe because they haven't interacted with anything.
That's correct. Yeah, right. They're just, so it really matters to us that we have mass. That's a fundamental feature of our perception of the universe. Our physics, if we were photons, our physics would be very different. I don't think we would be able to have the same kind of brain-like structure if we were photons, so to speak. I'm
just surprised that you don't place the brain as being necessary for the kind of thing that we do. Because I look at other organisms on Earth and I'm like, well, the trees aren't doing what we do and they don't have brains. And the brains of the other animals look very different from ours, even if you can point to somebody like the dolphins or the chimpanzees and they have kind of like a similar brain. But it seems somehow vital to the project to have a brain that does stuff, that's embodied in a way that lets you do stuff. Because like a photon can't build a detector because the photon is a massless object.
Yeah, right. I think, look, the fact is, the fact that brains work the way they do and that they lead to a single stream of experience, I think that's critical. Without the single stream of experience idea, you don't get the laws of quantum mechanics, you don't get relativity, you don't get a bunch of things. That's important to, and I don't know what other aspects of brains will end up being important to our perception of the universe. It's clear that the rough scale that we are at, the speed of our brains, the rough size that we have relative to the elementary length or relative to the whole size of the universe, that matters to our perception of the universe. Our physics would be very different if we were the size of planets. A lot of the things that we would have to talk about in our physics would be different from the ones we talk about today. And, I think, we're going back to old Isaac Newton, for example. It's interesting that what he picked out, and we talk about computational irreducibility and what can be figured out, even he picked out his laws of mechanics by separating just those features of the universe that he could have simple laws to talk about. Had he been doing fluid mechanics rather than rigid body mechanics, he would have gotten completely stuck. He did actually try and do some fluid mechanics, and he did get stuck because fluid mechanics and things like fluid turbulence work very differently. They are sort of in-your-face computational irreducibility. They don't have these reducible, you can just work out a math formula for what happens. So that was a kind of I think that was the thing that worked in those days. And it wasn't, we are living off these kind of pockets of reducibility. And this question of sort of why do we get these pockets, not other ones, and so on. I do think that things about the way that we perceive the universe, there will be other aspects of us that aren't assuming the answer, so to speak, that are that get us closer to seeing why it has to be that way for observers like us.
Is it possible that there are no observers other than us possible? In other words, that the universe has conspired to organize a bunch of atoms to sit in this room to have this observer experience in a way that is the only possible outcome
I think we're the only. If you ask, other observers like us, not in detail. I mean, could there be? How far away does the observer have to be like us enough that you think it's an observer like us, so to speak? So, for example, that we were talking about the worldview of the dolphins or whatever. Are they? One of the things that's important to us is, can we communicate with them? If they are minds that are, the way I would describe it, far away in real space, their view of the universe is very different from ours. If it is, the question of are we the only, we're not the only entities on which the universe has an effect. Many entities, the universe has an effect. In fact, pretty much everything that's in the universe is having an effect on. So insofar as being an observer is the universe had an effect on you, we're extremely far from being unique.
I see.
In terms of whether we are observers who, what attributes do we have? What do we have? We have this attribute, that attribute. We live a certain amount of time. We have certain biochemistry.
We have memory we can catalog our observations as well. It's like the rock, I'm not sure has that same sort of cataloging ability.
Really? What about all the scratches and cracks and things on it?
But it's not integrating them into like a cohesive picture, perhaps. I mean, I don't see how it has the infrastructure for that.
Like, can it change its behavior on the basis of getting a scratch? Like, can it move to a different place?
Well, it might do. I mean, it depends on what it can certainly break. It can do based on its experiences. It can have this whole, it can have, based on the experiences, this little piece got chopped off. That causes it to be, washed by the ocean in a different way. And this will happen, that will happen.
Can it move against gravity?
Or against the path of least resistance?
Well, I mean, that's a very Greek view of life.
I'm not saying that it isn't. I'm just.
That was the view of life. The uniqueness of life was that which can move itself. Until there were steam engines, for example, which also do a pretty good job of moving themselves.
Don't you need a guy who's in the boiler feeding coal for the steam engine?
Well, the steam engine has to be made by a life form, right? It's sort of derivative. But
well, you have to be made by a life form as well. I hate to point that out.
I think you can draw a line between synthetic and natural bodies.
Oh, that opens an entire 3-hour can of worms.
Yeah, right. No, I think that this whole question of self-reproduction and what that means and what counts as self-reproduction, I've been trying to study this a bit. One of the things that happens, in the computational universe of little programs and so on, one of the things that one has to get used to, which is very humbling, is these little, I always say, the computational animals are always smarter than we are. That is, you have some simple rule. You say, this thing is so simple, I know what it's going to do. It could never do this. And it turns out you're wrong. And I'm wrong over and over and over again. And I've been doing this for 45 years or something. And I keep on, even now, I will have, it couldn't possibly do this. So I've been interested in self-reproduction recently, and I've been trying to make minimal models of self-reproduction. The frustrating thing is that as I try to define the notion of self-reproduction, I keep on having these systems that cheat, in a sense. They do the thing that was my formal definition of self-reproduction, but I look at it and I say, that's not really, you're doing it in a trivial way. You're not doing it in the fancy way that is the way that I had in mind. So that's a tricky thing. I mean, I do think that with respect to biology, I think this kind of bulk orchestration mechanism, which I think will play into things like self-reproduction, it's an important kind of different theoretical foundation for biology. I'm not there yet, but I think it's findable.
Bulk orchestration sounds so much like a prime mover situation, though. It sounds so much like that will to move against the path of least resistance and the path of gravity.
I mean, bacterial replication is wild. They just kind of hit a point and then they double everything that's inside of themselves and then they split off. And so the process of replication is inherently able to capture the complexity of the thing because it just kind of pattern matches what it already has at each step until it hits some point where it's like, I've matched everything and now we're ready to go.
Right. But you see, the thing is, so these experiments I was doing on biological evolution, it's like you have some fitness function, you say, could it possibly satisfy this fitness function? I don't see how it's going to do it. You look at what it actually did. It's incomprehensible. It's just a random lump of computational irreducibility that it found. And there may be many of them. I mean, in what I've been able to do in those cases, I can actually map out all the ones it could find. So you can actually see what are the different ideas it had. This branch is like the reptiles. This branch is like the bacteria or something. They're different.
When you say they're like that, like I've looked at the hypergraphs, and
this is a different story.
This is a different story. Okay.
This is a story of my efforts in biological evolution, which has been informed by these things about hypergraphs, but it's not the same story.
Okay, so when you're saying that this is like reptiles, this is like fish, this is like birds, like what are you actually seeing from which you draw that conclusion? Is it
see these patterns of little colored dots? I mean, and they have they're very elaborate patterns that look very organic. They don't actually look like reptiles.
Okay.
What I mean by that is that you look at the thing and you say, let's say you're trying to make it live a long time. Okay. So how did it live a long time? Well, because this one had a thing that went back and forth in this very organized way, and eventually it died out. Okay. Whereas this other one over here, it makes this big structure, which eventually does this or that. Or this one has all this random stuff that it has in these little pockets, and eventually they all merge together and it dies out, let's say. So in other words, they have, in a sense, different ideas about how they work, which you can visually see. Just like if you look at the critters of the earth, they have different ideas about how to feed themselves or whatever else. And, they have different elaborate forms. This is very much the same kind of thing. It's remarkably the same kind of thing. And you can really see that, you can make these things where you show the kind of graph of all the possibilities. You can kind of see that, it could have gone this way, it could have gone this way. And you can kind of map out, you can even get, in these cases, you can look at, as you change the environment, you change the fitness function, you can see these guys were successful for a while, and then these ones take over, and then these ones were completely died out, and so they couldn't get to here, and so on and so on and so on. But it's what's to me very interesting about it is it's very simple. There's no, people have tried to make models, sort of mathematical like models of evolution before, and they always put everything in. They put, I remember in the 80s, people saying, we made a model of the rainforest and it has this feature and that feature. It's like, you don't say. You've got, 600 parameters here, and one of them represents, a tree frog or something. And of course it looks, does something a bit like the rainforest because you put all that stuff in. What's a surprise to me was that even models where you put nothing in, I mean, it's just these little bits that are being updated, you get a lot of these phenomena.
Okay, so then do you think that these things fold onto each other eventually to increase complexity, or because there's something about biology that's about merging, right? That's about the organism that starts as one species that mates across into a different strategy, and now there's some third form.
I don't think that's important. I don't think that, for example, I don't think the mating, sexual reproduction stuff is important. I mean, I looked at that and it just doesn't seem to be, it's, it has some effects. It's much more complicated to model. It has many more sort of parameters. What I was doing was just looking at pure mutation. So, and that's enough to give you, speciation, all those kinds of things. It's what you see is, in terms of you're saying, so one of the things you're implicitly saying, as Darwin famously said in the last sentence of Origin of Species, right? It basically says, as the Earth goes circling around the sun according to the fixed law of gravity, so in effect he says, more and more complex species are being produced. Okay, so he believed that natural selection implied increase in complexity. Nobody has ever figured out why that would be true. And it isn't.
Oh, well, he had to write that because humans had to be the most complex species on the face of the earth because they were built
in those days. Yes.
He did go to divinity school after all.
Yes. I think that that was, but I think he actually believed this to be the case. I mean, he talks about the formation of the higher animals. Okay, so he's not just thinking about humans. But I think that this idea that there's a force for increasing complexity is, I mean, you can see the extent to which that is and isn't true in these simple models.
It's not necessarily increasing complexity. I guess I'm just trying to, I'm trying to understand increasing diversity, right? So like in the model that you build, you begin with some kind of initial condition, and then there's some function that will inform each evolving system something about its mutational principles.
It's a very simple model. It's just saying, you're just mutating, single mutations. And you're just saying, what do you get from that? And you can ask, what are all the possible things you can get? And you have this whole graph of different possibilities. Sometimes they merge. More often it's a complicated, there's this complicated picture of what you get. And what natural selection is doing is in this graph, it is picking essentially a reference frame. What one would say in physics, a reference frame. It's picking what the set of things that it will consider to be fitter are. So there's a set of all possible mutations, and then it's kind of tipping it according to what it considers fitter. So it's kind of directing the flow of organisms in what we could call rulal space, the space of possible rules. It's directing the flow of organisms in a particular direction. And that's...
So do you treat organisms as just the sum total of their mutations, and they're this kind of like points-like information about their genetic state?
You have to see the pictures.
I do have to see the pictures.
I mean, okay. It's so simple. I mean, the thing that goes in is just so simple. It's just let's say a lot of what I study is 26 bits of information is the genome.
I'm just trying to figure out how to translate the thing that you're seeing onto the substance of biology, because you're seeing these patterns that emerge through a very simple set of rules.
Yes.
And you're like, I see them, and they're like birds, they're like reptiles, and I'm like, but they're also very different. Because you're saying that there's not actually a reptile in there. There's not actually a bird in there.
I gave a talk actually at Harvard Medical School a couple of months ago now about this stuff to a theoretical biology group. Okay, and it was fascinating for me because the best moment for me was when somebody who was paying a lot of attention. It's like 10 minutes into the talk. He says, "What kind of animal is that in?"
Yeah, exactly.
Right. But that moment, it was very, very useful to me because it was like, this is a completely different paradigm. The idea that you would have a kind of an idealized, abstracted thing is just bizarre. Just like for me, it would be, on the other side, it's like you're trying to find out something fundamental about biology. Don't study it specifically in the mouse.
That's a good argument to be made.
But I mean, I think that this question of what, how do you make the connection? Well, from my point of view, it's like, what kinds of questions could you ask in biology? I mean, for example, the idea of natural selection was asking a certain kind of question. The question I'm asking here is, how come evolution works? How come you can get to something which has high fitness? You might just get stuck. You might not be able to do it. Well, this explains how you can do it, and it tells you the way you'll do it. There are many ways to do it, and they will look very complicated. You will not be able to say, if you start asking, what is the mechanism by which the thing works? You'll be like, well, you write a whole biology textbook about it. Right? It is the explanation of why biology textbooks are thick.
I like that, and I understand what you're getting at, and I think that I understand why there doesn't have to be the direct.
Right,
you don't have to find the picture of the reptile in it.
Right now, I tried to. More recently, I did something based on this about foundations of medicine, which is something which I had no idea this would be possible. It's like medicine is not a field that has kind of foundations, really. It's like medicine is something goes wrong, you fix it, and so on. So here's an example of a foundational question. Are there a finite number of diseases? Right? And so most people who are serious practitioners will say, well, not really. We bin them that way because that's our billing codes or whatever else. But it's not, there's really a continuum of different things that can happen. But, what I was able to do was to just look at these basically, I say, let's consider an evolved system, a system that has evolved to behave in a certain way. And we run it. And then we say, let's poke it. Let's make a perturbation. Well, that will cause it to do different things. So you can look at all possible perturbations. You can ask, what's the mortality curve, for example? What effects do all these different perturbations have? You can map out what's the set of things that you can ask for the kind of the symptoms. You can say, what are the overall features and how much do these perturbations change the overall features? Like how much do they change the number of steps before the thing dies out? And you can ask and then you can say, well, then the fundamental problem of medicine is a perturbation happened that you had no control over. How do we make another perturbation that will kind of fix what happened before? And so that then becomes a question that you can have a computational answer to. You can actually start asking, how difficult is it? How much information do you have to be able to make that second perturbation? How successful can you be in doing that? And so on. So you begin to be able to have sort of an intuitional framework for thinking about how medicine works that is something very bizarrely different from what, the practicalities of, diseases of the, intestinal system or something.
Actually, I think that I have, with this example, I have understood something, which I appreciate very much, which is that you're basically creating this abstract topology of the influences on reality and how to shift those influences on the basis of fundamental rules.
Something like that.
Okay.
Yeah, I mean, I think I'm, the way I see it is, it's sort of okay, back in the 1600s, people had the idea, Galileo, Newton, other people had the idea, let's use math and let's apply it to understand the natural world. It wasn't at all obvious that something like that would work. It did work in the case of physics. It didn't work. People in 1800, there was this idea of social physics. One was going to solve sociology using physics. That didn't work. Biology didn't work to use, math to solve biology and so on. It's, what we've got right now is another paradigmatic idea, which is this idea of computation and following rules and so on. And there are many sub-ideas related to that. But the thing that is remarkable, and it's incredibly cool, is that a bunch of these different areas of science, when you hit them with that different paradigmatic approach, you start to be able to really say things about their foundations that people just said, oh, it's hopeless. We're never going to be able to say anything about these foundations. They just are the way they are. We can't ever explain them. And I think that's, it's pretty cool. I didn't expect this was going to happen. I mean, you asked me about the trajectory of how come I was working on fundamental physics. I said after the book came out in 2002, it's kind of like the market doesn't want a theory of fundamental physics. So, I'm going to work on other things.
They want a model of fundamental physics that lets them build a time machine, an invisibility cloak, an anti-gravity device, a fusion reactor. I think that the reason that example that you give about medicine is so powerful, because it suddenly gives a frame for something that's incredibly abstract, because you're like, evolution works this way and I have these simple rules and I'm like, I don't even know where to begin to fit that into my model of the world. But then you put it into something like medicine and it just seems so obviously useful.
Right.
And so I think that that's something that a lot of physics theories suffer from, which is like, where do you take this new understanding? Like, does it allow you to reach some deeper level? And so perhaps to close, does it? Is there an application for the Ruliad for physics like there is for this parameterization of disease for medicine?
Well, okay, so, working on fundamental theory of physics, my day job is building technology that people can use now, okay? We bring out a, big new product a couple of times a year, right? People can use it now. People say, well, fundamental theory of physics, what's its, horizon? I've been saying 200 years, okay? But it turns out I'm wrong. So I thought there'll be no applications of this stuff for 200 years. So I won't get to see any of them. But at least unless we solve some problems in medicine.
Well, they're working on it. That guy's like injecting his son's plasma and stuff.
Yes, I've run into him. I think anyway. It's, we can see if we can eke out a few extra years there. But in any case, the thing that was a surprise to me is it turns out the methods that were developed for physics can get applied to a bunch of these other areas. And that's a very powerful thing because physics has been so successful. Physics knows about things like black holes and so on. And that means that if we can make a connection at a more fundamental level between sort of the raw material of some fields like biology and the raw material of physics, then that means that we can take those things that have been discovered in physics and import them into these other fields. So, for example, the idea of reference frames, which, that's relevant to natural selection, which is totally bizarre. But because we know about how relativity works and how foliations of space-time work and so on, we can import that set of fairly complex, fairly sophisticated ideas into biology and make conclusions from it. So that's why it's important to have this sort of paradigmatic uniformity. Now, it's turned out that a bunch of things to do with physics, one of the things that hasn't panned out yet, but I think it might, is this question of like, people say, okay, how about making a business out of it, right? How about doing economics? Well, there's now 2 blockchains that at least claim that that a bunch of foundational ideas are based on things from Physics Project. So I was thinking about this too, and it's an interesting question, the extent to which the way economics works, the way that sort of the microscopic structure of the economic system with transactions and so on, how that builds up to kind of our things like the continuum notion of price, and the extent to which that's similar to the way that the structure of space is built from these microscopic, hypergraphs and so on. And so it's kind of that I haven't managed to close that loop. A couple of blockchain companies have built things on the basis of these ideas, and there's a whole raft of these things. Actually, it's kind of shocking how many companies there are now that have things that are sort of based on the concepts of the Physics Project. Not what I would have expected. But so, and that comes from, it's a paradigm that allows you to think about things in a different way. It happens to be applicable. Well, for example, I found out it is applicable to machine learning. It's also applicable to the foundations of mathematics. And really, the big power boost is this commonality of ideas from physics and ideas in these other areas. So in other words, like a weird thing is, black holes in physical space are like decidable theories in mathematics, a bizarre connection. There are many more of these bizarre connections that can be made. And I think that's so, if you ask a question like, will we have warp drive anytime soon? Okay. So I think the answer is no, but I think it's a more nuanced question than you might have thought. I mean, you might think, we know nothing goes faster than light. It's not as simple as that, because it depends on what space is like. In other words, it's very similar to what happens again in molecular dynamics. If we say, how long is it going to take for this molecule that, some little, molecule of something or other that, some volatile molecule of something is here, how long will it be before you can smell that molecule, right? So it'll be a while because it has to diffuse. It's going to go on micron. It's going to get kicked by another molecule. It's going to do this random walk to get to you. It'll take it a while. Okay? But if that molecule was able to be a lot smarter, it could figure out, well, I'm going to hitchhike, I'm going to piggyback on this molecule for the next micron. Then I'm going to switch to that molecule for the next micron. And it could find a way to plot a path where it would go at the speed of sound, because it's basically how fast molecules are going. Intrinsically, it could surf the structure of this molecular dynamics. If it could do things computationally in a sophisticated enough way, it could kind of make it across the room in much less time than you might think it should be able to make it across the room. So it turns out the same thing is true in space-time. If you could navigate, if you could pick which rewrite you wanted to be part of, if you could select which atom of space you were going to be kind of attached to, then you can go faster than light.
Because light can't choose?
Well, you can, the structure of space is such that it's, well, let's see how to say this. It's like with the molecules, when yes, something like light is doing the kind of thing that that the molecule has to do, kind of random walking from here to there. That's not quite an accurate analogy, but essentially, in order to, you have to kind of cheat the structure of space. Space is more like this thing which comes from all these different effects. And space has this definite structure. And so what you have to do is find these little paths through space that aren't going the average distance through space. They're this cheap way through space that you can find if you pick the exact right path. So the problem with that is, you say, well, that's great. So now we can make, a starship type thing. The problem is that the us doesn't get to fit through there. The thing that might be able to do that, even though it can't do it, so to speak, would be a thing at the scale of, atoms of space. It would be this thing that is doing all this computation down at that scale. If you say, can you take a human observer and stick them through this? The answer is not even close. No way. Just like we can't do, in principle, we could all be zooming around on, supersonic transportation, or at least speed of sound transportation, if we could hitch a ride on every molecule we decide is the right one, but we can't actually do that. And so what you realize is that there is, it's possible to have, faster than light travel, but not for us. Probably. I mean, one of the things that is the case about computational irreducibility is there are an infinite number of possible inventions you can make. So can I prove that there is no configuration of masses or something that would open up kind of a space tunnel? No, I can't prove that that's impossible. And my guess is that's basically impossible to prove. That's impossible. It will be one of these things that, like in mathematics, there are undecidable propositions that have sort of arbitrarily long proofs, where you don't know how long the proof might have to be. It's the same thing here.
And so is our goal to build machines or entities that are capable of doing the computational reducibility that allows us to actually access these places in the Roolead and these other configurations?
That's kind of what technology is about. Technology is, what is technology? Technology is you take what nature has given us and you find ways to apply it for human purposes. And, much of nature we don't know how to apply for human purposes. Some of it we do. We know how to mine certain minerals and, turn them into, memories or displays or whatever else. That is the story of technology, is to take what nature gives us, which ultimately is the Roolead, and figure out how to extract pieces of it that are for doing things that we care about doing. What we care about doing changes over time. What we care about doing is very particular to us. There's no absolute what we care about doing. The only absolute probably is if we don't exist, we don't get to do anything. So it's, that's probably the only thing we can say, is that we don't exist, the game's over. So I think this question of what are we doing? What is the story of sort of our civilization, technology, and so on? It's finding these pockets of reducibility. That is, and my guess is, actually, when it comes to economics, one of the sort of mysteries of economics is, how come the value of the world is continually increasing? And I think the answer is because we're mining more and more pockets of reducibility. We are finding more and more ways in which, so I think my current proto-theory of economics, which is not there yet, but the one thing that we as humans at the present time have a limited amount of is time. And human mortality means there's a time horizon for everybody. And so that, in a sense, what then matters is if you can do something, if you can beat computational irreducibility, you're coming out ahead. And in a sense, value is the beating of the computational irreducibility by finding these pockets of reducibility. And as we develop more technology and so on, we're finding more of these pockets. And I think you can kind of see, a view of sort of what If you say, well, what is human civilization going to achieve? Well, maybe we go plant flags on other planets, maybe other stars. That's pretty difficult. And it's pretty non-human by the time you're going to another star. It's pretty hard to have a regular human just sort of do that. And,
you need to bring a family of them at least.
Well, yes. So, it's kind of like when people are saying you're going to have a starship and it's going to be 14 generations or something. It's like whoever comes out at the other end, we talk about notions of purpose. Whoever comes out at the other end is not going to be doing the things that the people who went in 14 generations earlier thought they might be wanting to do.
Unless we have the Rulliad properly figured out and you can kind of poke at their motivational structures appropriately over the course of 14 generations.
Keep them tuned up.
Yeah, right. But no, I think that the picture is, we can explore physical space. We can also explore rullial space, which is basically saying we are finding different ways to think about the universe. We're finding different sort of viewpoints, different rules, we're expanding our domain, our intellectual domain of how we think about things. And so one of the things that sort of is maybe a kind of a be careful what you wish for thing, and sort of an ending type thing is, imagine you're in the Rulliad and you're gradually expanding your sort of points of view about the universe. You're essentially colonizing more and more of the Rulliad. And let's say that in the distant future, we've successfully expanded, just like we might colonize the galaxy, let's say. We're colonizing more and more of the Rulliad. The amount of the Rulliad that we currently occupy is vastly smaller than the amount of physical space that we currently occupy. Absurdly much smaller. We occupy some, we don't really know the scale for these things well, but we do know some bounds on it. It is clearly unbelievably much smaller than the scale that we occupy in physical space. But let's imagine that over the course of time, we could expand, our consciousness, so to speak, could span the Rulliad. Well, it's a kind of a be careful what you wish for, because at that point, in no sense do you really coherently exist. Your coherent existence depends on your specialness, so to speak. By the time you're kind of everything, you're no longer anything, so to speak.
And then God creates man all over again from the beginning because he gets bored.
Well, right. I think, one of the things that's sort of interesting, and you mentioned this earlier, is, there are a lot of questions that come up in modern science, and there are a lot of things which were being asked before modern science came along about, why does the universe exist? How did God make the universe? All these kinds of things. And then science came along, and science was very successful in certain areas. It allows us to build airplanes. It does all kinds of stuff like that. But there are still a bunch of questions that were pre-existing questions that science just I don't have anything to say about that, so we're going to ignore those questions. Now, we're in a better position to actually go back and ask and answer maybe some of those questions. And it is true that it's a funny thing about, there are lots of theological traditions that have had interesting things to say about the nature of the universe, the nature of humans relative to the universe, the existence of God, whatever that might mean. In a sense, the existence of the Rulliad is inevitable. There is a necessary thing. It's like there is if you think of it as a being, which I don't think one perhaps should, but there is a necessary being. And so that means and then the question, the existence of us, is a much more contingent thing. The existence of us in particular is very contingent. The existence of a thing vaguely like us, an observer a bit like us, is something one could imagine having a scientific way to say. There have to be in the Rulliad things that there are going to be inevitably things in the Rulliad that are like us. So then phenomena like self-reproduction become important. We're talking about, when you have objective reality and you don't have to have objective reality, you need a bunch of critters that sort of agree about what the objective reality is. And so that's a thing that, so you end up needing to understand, when you go from the Rulliad necessarily exists, do we necessarily exist? That is to some extent, scientifically answerable question. To what extent, in what fraction of the space of Rullial space is self-reproduction a necessary thing? Those kinds of questions are somewhat answerable, I think. I haven't answered them, but they're within the domain of things you might be able to answer. And questions like, why does the universe exist? So I claim it is inevitable and necessary that the Rulliad exists. So then the real question is, do we exist? It is not necessary that we exist in the form that we're in. But given that we do exist, it is, the existence of the universe is inevitable, so to speak. And that leads, when we were talking about Plato and so on earlier, one of the things that's an interesting...
I've actually felt like I'm sitting across from Plato several times in this conversation.
I'll take that as a compliment. I don't know, but he was wrong about many things. But no. I think the thing that one of the questions is: does mathematics exist? Is there a sort of a fundamental Platonic reality to mathematics? One of the consequences of all this stuff about the Rulliad is, if you believe that physical reality exists, then mathematical reality also exists. Mathematics exists. I didn't give the argument, but the basic point is that the thing that is all possible mathematics is the same object, the Rulliad. In physical reality, we are sampling some part of the Rulliad, and that is our perception of physics. In mathematics, we're sampling a part of the Rulliad as well. Mathematical observers have a different way of sampling the Rulliad than physical observers. But it is in the sense that, there is a thing there, and if you believe that there is something underneath physical reality that sort of is a thing, then so is it underneath mathematical reality. There's lots more to say about that, but
that's a deeply unifying place to end, which I appreciate, because I feel like it also opens a lot of other threads that perhaps we'll get to eventually. But I like the idea that it's not physics or math. It's that they supervene on something deeper, and that deeper thing is the thing that the multiple observers are trying to study and trying to understand. And you can model a mathematician and a materialist as being two different kinds of observers.
Yes.
So, I love that. We've done, more than 3 hours. It's been fantastic. I really appreciate you taking the time. I know that you're very, very busy, and it's been many years that we've been wanting to talk to you.
Well, this has been fun. We ended up talking about a bunch of interesting things. Thanks.
Yeah, thank you so much for giving us the time.
Really appreciate it.